Good morning. We'll give it a bit more time and then we get started. People are still joining, so okay. Let me start by sharing my screen and we'll get slowly started. If people are joining still later on, it shouldn't be too much of an issue. Okay, so again, good morning, everyone, and welcome to Scientific Python. We'll discuss a few things which are useful when you want to use Python for scientific computing. We'll talk about quite a number of things that are hopefully of interest. Okay, so let's get slowly started. Let me start by saying that if you have any questions, please type them in the chat. I'll as soon as it's appropriate. Someone is raising his or her hand. Probably to say that I'm still, no, I'm not muted. So, okay, I don't see who is raising a hand. So if there's anything you want to say, just type it in the, okay. So yes, you can raise your hand. I'd say, given that we are quite a lot, it's maybe easier to just type it in the chat. If it's not clear, or if you say, well, okay, I can't really ask my question in the chat, then it's no problem. And then I can ask you to activate your microphone and you can just ask your question verbally. So that's definitely not an issue. But maybe let's initiate that via the chat, just to make sure that things run more or less smoothly. But again, let me encourage you to ask questions. The more interactive this is, the nicer it is for me, and probably also the more useful it is for you. So don't hesitate to ask if you have any questions. Okay, so this is a QR code which you can happily ignore because I'm going to put the URL it actually points to in the chat. And let me also tell you what it is. So basically that is a small website which describes this particular training. But probably most interestingly, there is a link to a GitHub repository, and that contains the slides which are here, but also a directory called source code. And in that source code directory, you will find all the Python code which has been written to develop this training on the one hand, and also a lot of code for which I don't have time to discuss it. So yeah, feel free to clone this repository, to fork it. It's publicly available. The only thing is, yes, it's licensed, but that's a very mild license. If you use any material, please refer to it. Apart from that, you might want to stay in touch with us because this is a VSC training, so Flemish Supercomputing Center training. You might want to stay in touch with us via LinkedIn. Feel free to start following us if you don't already do that. That will keep you posted about upcoming trainings, other events in the space of scientific computing and supercomputing in general. Okay, so a few conventions throughout the slides, typographical conventions. Shell commands are rendered on a black background. Typically, there aren't many anymore in this presentation, but just for reference. So the dollar sign just indicates that you're in a shell. So basically, don't type the dollar, it's already there. It's just to remind you that that's a shell prompt. Similar for a Python interpreter. I don't think there are any Python interpreters commands anymore, but okay. So again, the triple larger than is just a prompt. Don't type it, it's just to represent that prompt. And similarly, of course, for an IPython session, again, same thing. The in whatever is, of course, just to remind you that that is a prompt. Okay, apart from that, in the slides themselves, inline code fragments are rendered in a monospaced font, just to make them stand out from the rest of the sentence. Longer code fragments are in the same font, but typically rendered on a gray background to make it stand out that this is code. Same for data files in this, I don't know, yellowish, greenish, slightly bluish, whatever color that might be. So same font, just a slightly different background to make code, to make it easy to tell code apart from data. Something that you will unfortunately see from time to time is this ellipsis here. It just means there is some more stuff which I can't fit on the slide due to, well, slide uh, real estate. And basically it means in the case of code, okay, probably I've been either talking about what is at the location of the triple dots before, or I'll talk about it afterwards, or it's fairly trivial. And anyway, for each code fragment that's in the slides, there is actually some code somewhere in the repository. So you're always able to find back the entire code and to look at it at your leisure. For data files, the triple dots simply means, yeah, okay, it's more of the same, and you can imagine what is going on here and how this code fragment will be continued. Okay, so that was a very brief introduction. I'm going to put the URL of the repository, well, of the web page in the chat again, because if you join a little later, you don't get to see the chat history, only the new messages. All right, so let's get started. And the first thing we'll discuss is NumPy. But first, let's have a little talk about why we are interested in libraries. There are, of course, many reasons, but one of the main reasons, especially in scientific computing, is that Python is an interpreted language and that Python is actually quite slow. And quite slow not only when compared to languages like C, C++, and Fortran, which are compiled languages and hence are in another league, but also with respect to other interpreted languages. Python is really not known for its execution speed, so it's really quite slow. Okay, question is whether that's a problem. Not necessarily so, of course. It's quite okay if you have a script that runs once, yeah, and performance is not necessarily an issue. It's certainly okay for prototypes. What I typically do is if I have to implement a new algorithm, which I'm not familiar with, is first do an implementation in Python, because you can program very fast in Python. You need few lines of code to get something done. So in that respect, Python is a very good prototyping language. So typically I'll implement an algorithm first in Python, and then when I'm sure that I understood all the in and outs of the algorithm, did some trivial optimizations, then I can start implementing it in another programming language, which gives me much better performance. But so again, for that purpose, Python is very well suited. I won't say ideal, but at least very well suited. If you have short runtimes and you run your script not that often, Python is fine. You don't care that much about performance. But for what it's not okay is for computationally intensive tasks. So typically, if you have long runtimes, if you have something that really uses your CPU, then Python might not be an optimal choice. So I would say don't use vanilla Python for heavy lifting computations. That's really not the best way to spend taxpayers' money. Let's quantify that a little bit, because it's always easy to say, okay, something is slow. Yeah, okay, could be true, but let's talk numbers. And we can do a small experiment. We can create a matrix, and that's done in an init matrix function. And as you can see, what I'm doing is creating a square matrix of random elements. Okay, so basically, our matrix is represented as a list of lists. All right, and then I have a second function, and in this I do a matrix multiplication. You know the drill. An element of the resulting matrix is computed as the sum of the elements of a row in A and the column in B, and the the column index in A and the row index in B must correspond. And you sum the whole lot, and that essentially gives you 3 nested for loops. The 2 outer loops and the inner loop. Okay, so that's all fairly trivial. That's code that's easy to write. Now let's do a little benchmark, and let's consider a 500 by 500 matrix, and that is not that large. Okay, so as you can see, the initialization function takes something like 1/10 of a second. Okay, whatever. And the matrix multiplication takes 32 seconds. Okay, what's your gut feeling? Is this fast? Is this slow? What would you say, just looking at that number or at these numbers? It's slow. Okay. Other opinions? Are there people who think it's fairly fast? You think it's fast. Okay. We have 2 slows, we have 1 fast. Super slow. Slow. Awfully slow. Okay. So most of you agree that it's slow to worse. Okay, let's try and quantify how fast we could potentially do this. And of course, this is a bit hand waving. The figures don't really add up, but it's just for the order of for the order of magnitude should be more or less okay. So of course, the whole thing is the heavy lifting is done in the inner for loop. That's pretty clear. And what we're doing in the inner for loop is multiplying 2 numbers and adding that to a third number. That's what we're actually doing. Okay, and then of course we are doing that many times because there is a triple nested for loop. So, but let's look at this inner statement. So whatever is happening in the inner for loop. Okay, so that's a multiplication and an addition. All right. Now the question is, how many of these operations can we actually do per unit of time? Okay. For that, we need to know a little bit about how a computer works. And of course, all of this happens in the CPU of your computer. The central processing unit is where all the computations are carried out. Okay, now when you buy a computer, when you buy a laptop, when you buy some other system, one of the things you're interested in is the clock frequency. So the gigahertz of your CPU. That's one of the parameters which you take into account, typically when you buy a laptop for scientific computing. Okay, but you may or may not be aware of the implications of that. You know that the higher that number, the faster things are going to go. Okay, that's true. There is no question about that. But okay, what does it imply? So basically, the number of gigahertz of your CPU determines how many elementary operations per second can be done. Okay, so basically that means that if we have, let's say for convenience, because otherwise we have to start using decimal numbers, we don't want to. So suppose we have 2 gigahertz frequency, clock frequency of the CPU. Okay, that means that you can do 2 billion 10 to the power 9 elementary operations per second. That's cool. And what's an elementary operation? Well, on a modern CPU, an addition and a multiplication are elementary operations. So they can be done in one clock cycle. It's not entirely true, but in this particular case, that would be actually the case. So essentially, that means that I can do 2 billion additions and multiplications per second. Okay. So essentially, that means that if I don't take into account really, really recent hardware, that I need, that I can do 1 billion evaluations of this inner loop per second. Okay, so how many times do I need to do this loop? Well, my matrix dimension is 500 by 500. So the outer loop, the second loop, and the inner loop both are 500 by 500 iterations. Okay, so essentially that means I have 500 times 500 times 500. That's 125 million times 2. So that's 250 million operations which I need to do in order to compute this matrix multiplication. Yeah, there is some extra here and there, but okay. Essentially, that's what it boils down to. So basically, that means since I can do 2 billion operations per second and I need to do 250 million, that this should take way under 1 second. Okay, so that's the potential. Not entirely true, actually, but okay, it's good enough. So we should be able to do way better than 32 seconds. That's clear. So given this back of the envelope computation, I'd say that the people who said that this was awfully slow actually seem to be right. So let's do the same thing, but now implemented in C, and then we see different numbers. So basically for the initialization, you see that it's like a factor of, I don't know, 6 faster. Okay, I don't care this much about initialization, but you see that the matrix computation drops down to half a second. Okay, so that is indeed already a lot faster. If we do this in Fortran, same implementation, you see that initialization is again a little bit faster, but not by much. But the matrix multiplication is faster by a factor of almost 4. So basically we go down to 0.1 second approximately. Okay, so yeah, this is not so very good for Python if we compare to C and Fortran. So clearly the Python implementation is not okay. All right. So yeah, we could say, okay, let's just switch to C and Fortran, which might be a good idea. No, I'm not showing a new slide. I'm still on slide 8. So that should be fine. Okay, so my question is now to you, why is this so slow? We already know Python is an interpreted language. So yeah, okay, that's something that we need to take into account, but still, it's still horribly slow. So what's going on? Because of the multiple loops, or there were multiple loops in C and Fortran as well. I did the same implementation. It's not necessarily a good implementation, but it's the same implementation. Just to compare apples with apples. So no, that's not why Python is slow. That's essentially why the whole thing is slow, but that's something else. Because also the Fortran implementation is still not optimal. Any ideas? Okay, so let's have a look at what is actually happening. And let's start by saying that, in fact, of course, I have been deceiving you. I have been deceiving you with words, and of course, that's always a pretty easy thing to do since natural language, unfortunately, is rather ambiguous. So I have been talking about a matrix. And if you think about what a matrix is in mathematical terms, then that is a structure that contains elements, and all these elements have the same type. They also kind of represent some data which belongs together and which you think of as one mathematical thing which is compact in a way, for whatever definition of compact we're using here. Again, this is fuzzy language, but yeah, the mathematical matrix thing is something somewhat abstract. So basically, if we translate that into how we think about it, then things get fuzzy just by definition. But I already mentioned that my matrix representation is in fact a list of lists. Okay, but one of the typical things which you have if you think about matrices is indeed that they are matrices of real numbers or of integers or of rational numbers as far as I'm concerned. I don't care. But at any rate, all the elements have the same type. But for a list in Python, that is not necessarily the case. I can have a list that of which the first element is a double precision number. The second element is, I don't know, a string. The third element is a list, etc., etc. So Python cannot assume upfront that all the elements in a list have the same type. It has to check for each element what the type is. Okay, that's already a bit of a bother, because that means if we start to look at this expression, then we have to check first that A is something we can in fact apply the square bracket operator to. In other words, A is something that we can index. Now, yes, that is the case because A happens to be a list, and I can index a list. All right, so that's already one check which I have to do, but okay. Then I need to see whether I is something that I can use to index a list. I happens to be an integer. Okay, I can use an integer to index a list. Okay, second test passed. Then I need to check that the value of I is in an acceptable range. Okay, so that means that I should be larger than or equal to minus the length of the list and less than the length of the list. Okay, that's also the case. Next test passed. Okay, whatever the result of AI is, I'm again applying a square bracket operator. So it should be something that I can index. Yeah, because AI is in fact a list. So again, that test passes. I need to check the type of K. I need to check whether K is in range. I need to do the same thing for B. I need to check whether A, I, K, B, K, J can actually be multiplied. Yes, they're both floating point numbers. Then I need to start doing the whole thing for C. And then I need to check whether I can actually add to whatever this thing is a floating point number. Yes, because this also happens to be a floating point number, so all of this works. But I have been talking like 1.5 minutes, probably 2 minutes, in order to just list what tests that Python needs to do in order to carry out one iteration of this for loop. And there are 125 million of those. So that is a lot of tests that Python needs to do. And hence Python is slow. And the reason for that is essentially that we are using a crappy representation of matrices. We are using lists of lists as a representation for matrices in Python, and that is a terribly bad idea. That is very naive. Okay, so what can we do? Well, one of the things we can do is use a library which has good data structures for scientific computing. And of course, the major thing we need typically is fast matrix operations. So we need a good implementation of arrays. Okay, and NumPy is one of the libraries that actually offers us that. It offers us an implementation of arrays that is pretty fast. It offers us matrix operations, BLAS-like, on these arrays. It offers some linear algebra, fast Fourier transform, mathematical functions that are defined on those arrays, fast pseudorandom number generation for various distributions, simple statistics. And if I'm saying simple statistics, I mean descriptive statistics, so really trivial stuff if you're a statistician. And all of that is in the NumPy library. There are other libraries as well, which we'll discuss later. So basically, let's rewrite our initial problem, but now using NumPy. And as you can see, things get a lot easier. The first thing to do is to import NumPy as NP. You don't have to do that. You can just import NumPy, but you will see if you check for answers on Stack Overflow or wherever, everyone is using NP as an alias for NumPy. What you see sometimes, but which I would really encourage you not ever to even consider, let alone do, is from NumPy import star. Please don't do this. You will shoot yourself in the foot at some point. Never do blanket imports. Okay, so import NumPy as NP, and then we can use all the functions which are defined in the NumPy module. Okay, so our matrix initialization now is done using NumPy. NumPy random, uniform, lower bound, upper bound, and the shape of the array which we want. The shape is n by n, so we have a two-dimensional matrix with n rows and columns. Okay, so this is already, on the one hand, much less code than before, which is a good thing. And on the other hand, it also means that now we have a NumPy array rather than a list of lists. Okay. Our matrix multiplication becomes a lot simpler. We can just do A at B, and at here is the multiplication operator, which works on NumPy arrays, but also on arrays that are defined in the Python standard library. The Python standard library also has a module called array, which in general you might want to avoid like the plague, because there are several reasons why I really hate it. But nevertheless, it's there, and okay, the add operator would work. And this is the matrix multiplication, actually. Okay, so let's time this again. So NumPy gives us 0.011 second, so that is really close to the Fortran number. And the matrix multiplication is even faster than Fortran. Fortran was 0.11 seconds, and now NumPy is in fact 0.77 seconds. So a rather huge speed increase. And we're still doing Python, only instead of doing Python, we're in fact using NumPy under the hood. Okay, so to summarize, Python took 32 seconds, C took half a second, pure Fortran took 0.1 seconds. If I use Python, well, NumPy in Python, I get below 1/10 of a second. And of course, if I use Fortran in combination with BLAS, I get the best performance by a small factor compared to NumPy. Sorry, I'll go back to this. My mouse did something weird, or I did something weird with my mouse. So why is the BLAS thing here? Well, essentially, when we go back to the previous slide, one of the things I said, okay, BLAS-like operations. What do I mean by that? Well, there is a library which is commonly used in scientific computing, and that is BLAS. BLAS. Yeah, memory fails me. What's the B for? Damn. I say this 100 times, and now my memory fails me. Basic, yes, thank you. Damn, I really couldn't remember. This is really stupid. Because I really say this 100 times per year, and sometimes, yeah, it just vanishes from memory. Okay, yes, the basic linear algebra subsystem, and basically that is, yeah, exactly. Well, yeah. So sometimes things just disappear from memory for a short while, and then it takes a while to get it back. Okay, so basically that is a library. Well, there are many implementations of it, but it basically means that you can do fast matrix operations. And you have several levels of the BLAS library, level 1, level 2, level 3, where level 1 is operations on vectors, things like normalizing vectors, scaling vectors, stuff like that. Level 2 operations is matrix vector operations, for instance, multiplying a matrix and the vector. And level 3 is matrix operations, so for instance, a matrix operation. I'll answer your question about MATLAB in a minute. So under the hood, NumPy is typically going to use a BLAS library. And one of the things you have to take a little care about is which BLAS library is going to be used. How do you know? Well, if you are on one of the VSC supercomputers, one of the VSC clusters, and you use the module system in order to get Python, then you can be quite sure that a good BLAS implementation is going to be used. If you have a Python which is built with FOSS, it's going to be OpenBLAS. If you have a Python which is built with Intel, it's going to be Intel MKL. And both are good implementations. If you use Conda, you have to make sure that you've got the right one. Typically the right thing happens, but let's check. So normally, this is on my system. Let's see what list says. Okay. Now, let me just, to get a little bit reasonable formatting, because otherwise it's too hard to read. So let's go down, and one of the things which we see is normally OpenBLAS. Lib OpenBLAS somewhere, yeah. So as you can see, I've OpenBLAS here. So basically that means that normally NumPy should use that, and that I'm pretty sure that I get good performance. If you see somewhere libnetBLAS, run for the hills, because that's the reference implementation. It will work, but it's very slow. So you should really see something like libopenBLAS or MKL. That's also fine. MKL would mean that it's the Intel thing. Okay, so here I'm using OpenBLAS. Okay, of course I can also use the BLAS library from within Fortran, and then you see I get still a bit better performance. But the main message here is that if we go from Python to Python and NumPy, we have a 415 speed increase for this particular problem. That does not mean that any and all Python code you have, just if you start to use NumPy, is going to be 100 times faster. Absolutely not. But for this particular case, it's pretty impressive. And in general, it's you gain quite some performance if you use NumPy as array representations and array operations. We'll see a few performance pitfalls when we proceed. MATLAB, to return to the question in the chat, depends a little bit. I haven't benchmarked it here. It should be somewhere around Python NumPy if everything goes well. It should also use a proper BLAS implementation under the hood. I didn't do the benchmarking. I'm not really a MATLAB fan, and hence I prefer not to use it if I can avoid it. So if you're a MATLAB person, no problem. If you're happy with it, keep on using it. But yeah, personally, I don't like it much. I don't like the implementation. I don't like the syntax, but that's a personal thing. Okay. Yeah, sure. It's definitely useful. I'm absolutely not saying that MATLAB is not a useful thing. It's just not my tool. And that's in part personal taste. So this is not a religious thing. It's just a matter of taste. And yeah, I think that if you come from a computer science background, that MATLAB is jarring a little bit somehow. It's a matter of how it's implemented, how it's designed, which kind of, yeah. Okay. And by the way, as a MATLAB user, you will recognize quite a number of things in NumPy that have been borrowed or inspired, however you want to call it, by MATLAB. So as such, as a computing device, MATLAB is definitely a good thing. So don't get me wrong there. It's not because I don't like to use it that it's not good. Okay, so performance-wise, my guess is that it's approximately on par with Python NumPy, maybe a little bit slower, but okay. Do your test. I mean, just do the thing with a 500 by 500 matrix and see what it does. It's a good thing to do. Okay, so before we get started into how to use NumPy, let me first do a little poll and ask what your background is. I want a multiple choice. Okay, so what is your primary programming language? And I'm asking just to be able to know which languages I need to refer to. So MATLAB is obviously already one. And of course, you could also come from an R background and all the rest. So C, C++, or Fortran. Okay, let's start a poll. That makes it a little easier for me to refer to other things when I'm comparing. Well, when I'm introducing features, that I can say, okay, if you come from this background, then be careful because this is going to be different, etc., etc. If you have some other background, you can also type it in the chat, because yeah, I only have 5 options, so you can do more than 5 options. Okay, so basically most of you have a Python background, Java, okay. Then many people are using MATLAB, and some people are using R, and then there is some Fortran and probably some other languages indeed, like Java. Okay, so that is interesting information. So MATLAB people will recognize quite a bit. All right, so as I already mentioned, if we want to create arrays or whatever we want to do with NumPy, the first thing we always do is import NumPy as NP. And that is really convention. And I would strongly encourage you to follow that convention. Sorry, otherwise I don't see the chat. Follow that convention because it's all over. I think that approximately, I don't know, 99% of what you will find on internet is using this convention, whether they show this statement or not. Okay, so we can create arrays very easily. For instance, if we want an array filled with zeros, very easy, np.zeros and the number of elements you want. So basically, the first statement would give me v1, which is an array with 3 zeros. The same with ones, and we also have empty. So why would you have empty? Because that sounds a bit silly. Why not just take zeros if you want an empty matrix? Well, one of the things that you should realize is that getting something from memory or putting something in memory is in fact fairly expensive. And fairly expensive, that means in comparison with the number of computations you can do in the same amount of time. Now, and we will see an example of that, you create an array and you fill it with zeros, that takes some time. If you create an empty array and then later fill it with other values, and you would ignore the initial values in the array, then you're wasting some time if you initialize your array with zeros. So that's why the empty thing exists, and I'll give you an example of that later. So maybe let's just experiment a little bit. So here I'm in my shell, this is my computer. I have loaded an environment, and by the way, that environment is also available to you in the sense that there is an environment YAML file which allows you to install almost all the packages that are required by the code in this repository. There are some subdirectories that have their own environment because it gets a little large and basically that gets a little unwieldy. So you can always reproduce things. So there is also a spec file, but that only works on Linux. So the environment file should work, environment.yaml should work on all systems, and the spec file is only for Linux. Okay, so in this environment, I do have Jupyter Lab, so let's start that. And let's see where this thing gets opened. Of course here, which is not what I want. Let's detach this and let's set it up a bit. Okay. So I'm just going to start an empty notebook. All right. And let me simply create an array A. This is weird. Okay, it's probably because this is, probably can't. Yeah, I'm not going to zoom out. I'm just going to live with the weird formatting. Okay, so let's say A is np empty, and I want 10 elements. Okay. Yeah, of course, I'd better import NumPy first. Okay, and now I want to not have this double A. Okay, so let's see what the value of A is. And then you see that there are some values, but they're a little bit weird. Okay, that just means I got some chunk of array where I can store 10 numbers, but whatever was there in that chunk of memory is now interpreted as a floating point number. And as you can see, we get some rather weird values. Some of them are very, very large, like this one. Some of them are very close to 0. Some of them are 0 or almost 0. So basically, if you have an empty array, you don't know what's in there. You have to initialize all the elements yourself. But there are sometimes good reasons to do that, as we'll see. Okay, you can also create two-dimensional arrays very easily. So the thing you do is you simply specify a tuple with the dimensions. So in this case, it's a two tuple. So we will get a two-dimensional array, so a matrix if you want, with 2 rows and 3 columns. All the elements will be equal to 0. All the elements will be equal to 1. This will create as a identity matrix. And of course, an identity matrix is by definition square. So we only need to specify the 2, which basically means I get a 2 by 2 matrix. All diagonal elements are 1. All off-diagonal elements are 0. And again, we can do an empty matrix as well. Okay, so that's very easy. The default type is NP float, and that would be double precision. So we'll come back to types in a minute. There are, of course, other ways to create arrays, and one of them, for instance, is to initialize elements randomly. And we've already seen an example. So here we use the random module in NumPy, and we use the uniform distribution. So the first argument of uniform is the lower bound of the numbers which we're going to generate. 1 is the upper bound. And then you can specify the size or the shape of the resulting matrix. And again, this would be 2 by 3, so 2 rows, 3 columns. Each element a random sampled from a random uniform real distribution between 0 and 1. Okay. You can also use a list of lists, or in case of an one-dimensional array, a list of numbers, and then this gets translated into an array. Let's do that, because typically I prefer to format that a little bit differently to make it a bit clearer. So for instance, A would be NP array, and I would have a row 1, 2.3, 5.1, 2.5 minus 0.5 and say 1.3. Okay. And this gets displayed in a reasonable way. As you can see, I've got 2 rows, 3 columns. So don't be deceived here. This looks like a list of lists, but no, it's actually an array. As you can see here, this is really an array. Okay, so that's the way you can initialize small arrays just from lists. Later we'll see an example, well, not really an example, but something that happens under the hood, where an array is indeed initialized as a list of lists and where that is an extremely bad idea. Okay, so you can also very easily create arrays out of files that contain text representations of floating point numbers. For instance, this is our data file, and it just contains 2 lines. Each line represents a row, and we have 3 columns. So basically, this would give us again an array with 2 rows and 3 columns. So that is very convenient. And gen from text is a really versatile function. It also allows us, for instance, to set the separator between consecutive column elements. So we could set that to a comma. It also allows us to set the delimiter at the end of the row. So if our data would be arranged in a different way, for instance, a row and then a semicolon and then another row, we could also specify that. So that is all quite convenient. So if you look at gen from text, if you look at the help, you see that it takes like a million arguments, and you recognize a few things that can be nice. For instance, skip header. So if your text file with data contains some header rows, you can skip those. Similar for footer. You can specify what to do with missing values, etc., etc. So basically, there's quite a lot you can do. The delimiter here, as you can see, what denotes a comment and so on. So basically, there is a huge help file or a huge help string for this particular command. Okay. So all of these are ways to create arrays. Maybe let me show one more. So if I want a one-dimensional vector, I can of course also do that from a NumPy list, from a Python list. For instance, 3.1, 4.5, and 7.8. So that would also give me a one-dimensional array in this case. Okay, if I would like a three-dimensional array, well, an array of, yeah, three-dimensional array, I can also do that. For instance, v would be np.array, and then I'd get a list of lists of lists. So this would be my first row. And so on. Okay. Okay, I have a syntax error somewhere. I think this is too much. Yeah, okay. And then, oh, this is also too much. And that is too much. That is too much. And I've lost track. I think this way it should be sort of okay-ish. I hope. Nope. Okay, now I have to start hunting for which one I forgot. Here is it. This is wrong. Okay, here it is. All right, that's better. So now how does that get rendered? Not in a very easy to understand way, but still Python does its best. So basically this is now a 2x2x2 three-dimensional matrix. Okay, so thanks for spotting the mistake. Okay, so that's quite easy to do. There are a couple of functions which you may recognize in the sense that we have an arrange function, and that essentially allows us to specify an initial value and an end value and an increment. So this should remind you of the Python built-in range function, and it has the exact same semantics. So the range function in Python, as you know, also can optionally take three arguments. Always an end value, then the starting value is by default 0 and the increment is by default 1, or two arguments and then the first argument is the initial value, the last argument second argument is the end value, or three values, then you have an initial value, an end value, and an increment. So basically a range does the same thing. You have an initial value, in this case -1, an end value 1, and an increment 0.25. And the semantics is the same as range. So the last value in range is that of the end -1, or end, it will be less than end, let's put it that way. So it's the same for a range. So we start with -1, then minus 0.75, because the increment is 0.25, and so on, and we go up to 0.75. So not 1, because if I add 0.25 to 0.75, I get 1, which is not less than 1. So the last value is not included. Okay. So that's the same as range in Python, and it seems nice. Except that it's not necessarily nice. What could be an issue here? Well, an issue is that I'm dealing with floating point numbers. And the problem with floating point numbers is that, yeah, it doesn't go all the way to 1. Yeah, it depends on what I want. It might be that that is exactly what I want, because that's exactly what happens in Python with the range function. So in that respect, it may not do what I want, but then that's easy to solve. If I want to do that, I can of course solve this. What I can do is say, well, okay, np arrange. Let's try to spell that correctly. I start at -0.1. I really want 1 included, so I'm just going to put something like this, and then 0.25. And indeed, now 1 is in fact included. So, okay, I need to think a little bit, but I would say that that is the same as something like, okay, range. If I want 5 included, I'd also have to do 6. So it's the same thing which I would have to do in Python itself with the range function. So for Python people, it's not that weird in a way. But the real issue is that in fact I'm dealing with floating point numbers. And what I'm doing is comparing a computed value with the end value. Now, of course, floating point values are the result of computations. And all those computations can lead to round-off errors. So it might be that due to round-off, depending on the step size, that I actually end up with one element less than I would expect, or one element more than I would expect, depending on what I'm expecting. But basically, I'm never 100% sure of the number of elements which I will get with a range. For simple cases, yes. For instance, in this case here, I'm really sure that I'm going to get 7 values. 1, 2, 3, 4, 5, 6, 7, 9 values. Okay. So basically, I'm pretty sure. In this case, I'm also reasonably sure, but maybe not even 100%, that I will end up with 8 values. 1, 2, 3, 4, 5, 6, 7, 8. So I'm not 100% sure here. In this case, I'm sure. But for, let's say, more intricate cases, I'm not quite sure. So that's why a range may not be your friend in all circumstances, but there is another function which MATLAB people will recognize, and that's linspace. And that gives you evenly spaced, linearly spaced if you want, values between the lowest and the highest, and those will be included. And this is the number of elements. The third element is the number of elements which you will get. So basically, if I want to make sure that my lower bound and my upper bound are part of my array, it's much safer and much easier to use linspace, especially since I'm 100% sure how many elements I'll get, because that's what I'm specifying. So this is a much safer operation in many circumstances. I will use a range from time to time when I know there is no danger of round off tripping me up. Then I'm going to use a range for certain purposes, but typically I'll be using linspace. Okay, let's talk a little bit about data types. So NumPy has a lot of data types. For integers, there are something like, let's see, 8, I think. So basically, we have np int 8, np int 16, np int 32, and np int 64. And the number here stands for the number of bits that's used to represent that integer. So essentially, let's look at np int 8. That means we have 8 bits. With 8 bits, each bit can be 0 or 1. We can represent 2 to the power 8 integer values. 2 to the power 8 is 256. Okay, so that means since integers are signed, I can represent numbers from minus 128 up to 127. Okay, so similar for int 16, we can represent numbers from minus 2 to the power 15 up to the power 15 minus 1. So that is of the order of 32,000 something. NP32, that's minus 2 billion to 2 billion. And of course, int 64, that's, well, minus 2 to the power minus 63, minus 2 to the power 63 up to 2 to the power 63 minus 1. So that's for pretty large integers. Okay. Now, you can use npint without specifying the number of bits, but I would not recommend this because it depends on the architecture and also the operating system which you're using, whether npint is going to be an npint 32 or an npint 64. So on Linux, it's going to be 64 bits. Typically, on 46-bit architectures, so if you have a CPU that uses 64-bit architecture, and there's actually absolutely zero chance that you would have something else in this time and day, except if you're on embedded CPU, on embedded processors, then you might have something different. But for any general purpose machine, you will have a 64-bit architecture. However, the last time I tested, and admittedly it's like 2 or 3 years ago, if you run JupyterLab, for instance, on Windows, then it would default to int32, although clearly you are using a 64-bit architecture. So still, my recommendation would be don't use npint, always be explicit, whether you run 32 or 64 bits. And of course, for every integer type, you have its unsigned equivalent. So for instance, an NP unsigned int 8, so a uint 8, would be from 0 to 255. For a uint 32, we would go from 0 up to 2 to the power 32 minus 1. And that would be 4 billion. Okay. Why would, for instance, we use an NP uint 8? When would such a thing be useful? So that would give us numbers between 0 and 255. Well, one of the things we could do with that is, for instance, represent colors. Because if you look at RGB, red, green, blue, then that's a 3-tuple of numbers between 0 and 255. So basically, if I use 3 uint 8s, I can in fact represent RGB, the RGB color space. Why would I care? Because I can just as well use NP int32 for that, or even NP int64. They can also represent numbers between 0 and 255 and infinitely, well, not infinitely, but many more. So why would I care about which integer type I use? Yes, it takes less space, exactly, memory. And of course, in scientific computing, memory is a concern. If you can represent your image, suppose we're doing image processing, and if you can represent each pixel by 3 times a byte, because 8 bits is a byte, versus 3 times 8 bytes, as for NP int64, that basically means that you have a factor of 8 more memory if you use uint64 versus uint8, and that is a lot. So indeed, it's very important to choose your data type appropriately to conserve memory on the one hand, and of course also to get the best performance out of your memory subsystem. If you're really interested in the details of that, one of the coming weeks there is a training, code optimization, and that will talk in a lot more detail about these kind of things. It's not Python specific, it's general for all programming languages. Okay, so floating point numbers. We have actually 4 floating point types, 2 of which you will be familiar with. So the float 32 is single precision. The float 64 is double precision. Single precision means you have numbers between, well, up to 10 to the power 38. Smallest non-zero number you can represent is 10 to the power minus 38. And you have 6 to 7 digits of precision. So for NP float 64, that's double precision. You've got 15 digits, 15 significant digits, and you can represent numbers up to 10 to the power 308. Smallest non-zero number is 10 to the power minus 308. So those are your typical floating point formats, your typical floating point types, which you have in most programming languages. Then there are 2 extra ones. One is NP float 16, and the other is NP float 128. And as you can already guess, float 16 is going to use 16 bits only to represent a floating point number. So that gives you only like 3 to 4 significant digits. And for the life of me, I don't quite remember the exponent which you can actually store. Because typically what you're interested in here are really the digits, not so much the order of magnitude. Where are they used? Well, typically they're used on GPUs. Because it turns out that if you have a neural network, a deep neural network, that actually if you use it for inference, it's actually a good idea to train it in, let's say, single precision, and then convert that network into a more compact version with half precision, and you gain quite a lot of memory because your network needs less memory to be represented. So that's why, in a way, half precision floating point numbers were introduced into modern hardware. So they don't work, well, okay, they do work on CPUs, but there is no hardware support for that, except in the very latest generation of Intel CPUs. So Sapphire Rapids, if memory serves, has hardware support for half precision. Okay, so that means probably that float 128 is going to be quadruple precision. And indeed, that's the case. You've got 31 significant digits, and you can store up to 10 to the power 4,000 something something as the largest number. That seems nice, but unfortunately, again, there is no hardware support for that. So basically, that means that if you use NP float 128, you're going to see a significant performance hit. So on CPUs, I'd say avoid float 16. unless you are dealing with data that somehow comes from or goes to a GPU, then it might make sense. But for pure computations on a CPU, don't use it. And similar for quad precision, avoid it if you can. Okay. So again, there's a default NP float translates to float 64, but yeah, I wouldn't bother with NP int or NP float. I just always specify the number of bits. We also have complex numbers, and this is a little bit confusing. So we have NP complex 64, NP complex 128, and NP complex 256. So don't get confused. NP complex 64 is in fact single precision. We use 32 bits for the real part, 32 bits for the imaginary part. So if there are people who come from Julia, there it's different. So double precision is indeed complex 128. So those are first class citizens as well. We also have Boolean values, NP bool. You might hope that that's a single bit, but no, each Boolean value actually takes up a byte, so 8 bits. And then there's character data, and again, that is 8 bits, so it's a byte per character. Okay. So how do you use that? Well, you can always, well, not always, but with most functions in NumPy that generate arrays, you can specify an optional dtype argument, and you specify the type which you want to have. So that's very easy. By default, you will get floating point values. How can we know? Well, we can always ask for the dtype of something. So for instance, I had here an array V and an array A. So let's check which type they have. And the array itself knows. I can just get the dtype. The dtype attribute. Note this is not a function, this is really an attribute. And as you can see, it's a float 64. If I do the same thing for A, I'll get actually the same result. Now let's do that for B. And you might notice something that you maybe don't expect. It's an int64. Okay, why? Well, normally you get floating point values, double precision, when you create matrices. There are a few exceptions. So one of them is if you create a NumPy array out of a list of lists, and that list contains only integer elements, then you will get an int64. And the same applies for a range, for instance. So np arrange with 1, 5, and say 1, that is going to give me an integer NumPy array. As you can see, it's int64. So whenever I'm talking about programming languages and about best practices, one of the things I always mention is that if I write a constant, a floating point value, I'll always append .0 to it. On the one hand, that visually reminds me that this is a floating point value. I don't have to think, oh, there is 0 here. What does it mean? Is it integer 0 or is it floating point 0? There is 5 here. Is that an integer or is that a floating point? If I intend it to be a floating point, I'll write 0.0 or I'll write 5.0. Okay, it's a bit more typing, but it's less confusing. I'm 100% sure that the constant I'm looking at is in fact a double precision number or is an integer, or at least intended as such. And here, not following that, what I would call best practice, actually can lead to very unpleasant surprises with respect to performance. So because under the hood, of course I could work with this, but then under the hood some conversions would be needed, because probably at some point I would start doing floating point stuff, and then we need to convert our integers to floating point. And then that takes time. It would have been smarter to create it as a floating point thing in the first place. So something to be aware of. Let me really show you the difference. Let's do np arrange again. No. Okay, let me do it differently. Where's my arrange thing here? Okay. So basically, let me. Okay, I'm copying the wrong thing. This is a really confusing now with this, because I don't see what I'm doing. The formatting is rather annoying. I think I really have to go down to 1%, 200%, because otherwise this is really too confusing. I can't read it anymore. And this is weird. Something's okay. I collapsed this thing. That's the reason. Okay, so let's do this. But now let me add dot zero thing. And you see immediately visually that this is an array that contains floating point numbers, because there is a dot here. See? And if I check the dtype, then you see that indeed now it's float 64. So that's something to be aware of, and something that can cost you performance if you don't take care of it. Okay, how do you access array elements? Well, basically we use the square bracket notation here. So basically I can do something like this, v1, and that will give me the second element. Let me remind you what v is. So that gives me the second element. So as in Python, list indexes start with 0. In NumPy, array indices start with 0. So that's of course something to remember if you come from a MATLAB background, from an R background, from a Fortran background. Indices in those languages by default start at 1, not at 0. So for Python people, it's fairly straightforward. If you come from a MATLAB background, you have to remember. Okay, so v1 is the second element, not the first one. And of course, I can also assign to v1. I can put minus 1.3 in there. And then you see that the corresponding array element has been changed. So I would say no surprises there. If I have a two-dimensional array, I just specify the row I want and the column I want. So I have to be a bit careful. It's a 2x3 matrix. So now I have the second row and the third column. Okay, so basically, as you can see, that is indeed what we got. All right, so that's very easy. So we have something which is called the shape of an array, and that gives us the dimensions. So the shape of v1 of v rather, that is going to be a 1 tuple with essentially the length of the one-dimensional array, but it's a tuple. So if I want a number, I should use the 0 index, and then I really get a number. If I have a two-dimensional array, the shape is of course a two-tuple. If I have a three-dimensional array, the shape is going to be a three-tuple. Okay, so that's nice. NumPy array knows about its type, it knows about its shape. That's very convenient. Okay, we can also ask for the strides. So we have an array with 2 rows, 3 columns, and if we ask for the strides, we get 24 and 8. Okay, what could that mean? Because these numbers might seem a little odd. but you can make sense of them if you know two things. You know the shape of the array, 2 by 3, and you know that each element of this particular array is going to be a float 64, so that it has 8 bytes. 24 happens to be 3 times 8. These numbers could make sense if arrays, two-dimensional arrays, are stored row by row, because then the first number would be the number of bytes I need to move to get to the next row. Okay, let's see whether that makes sense. If my array is stored row-wise, let's go here for a second, and then of course, to go to the next row, I would have to move 8 bytes, one floating point 64, another 8 bytes, and another 8 bytes. 3 times 8 bytes, 24. The second element of the strides was 8. So that could mean moving to the next column. And indeed, that's just one floating point 64 away. So basically, just one, it's just 8 bytes away. Okay, so if that interpretation is correct, then indeed, in NumPy, arrays are stored row-wise. So basically, that means that in memory, A is represented as 1, 2.3, 5.1, 2.5, minus 0.5, 1.3. And indeed, that's how NumPy by default stores arrays in memory. This is different from MATLAB, R, and Fortran, where A would be stored in memory as 1, 2.5, 2.3, minus 0.5, 5.2, 5.1, 1.3. So column-wise. And that's another very dangerous false friend. If you translate algorithms from R, from MATLAB, or from Fortran to Python, keep in mind that the way two-dimensional arrays are stored is fundamentally different. And again, that has nothing to do typically with correctness of your algorithm, but for performance reasons, you really need to know what the layout of an array in memory is, a two-dimensional array in memory is. So that's an important one as well. Okay, maybe let's have a look at the strides of B. No, it would not show. No, it would not show a difference. That's not a good idea. But maybe let me make another two-dimensional array. And just for simplicity, I'm going to use zeros here. And I want a two-dimensional one, so I need to specify a tuple. Okay, and again 2 by 3. Oh, sorry, no, that's not what I want. I actually want to specify the D type explicitly. Okay, so the D type would be NP and int 8, for instance. Okay. And if we ask for the strides now, you see that we get 3 and 1. Indeed, each element is just a single byte. So in a 2 by 3 array, move to the next row, I need to go 3 bytes to the right. To go to the next column, I need to go 1 byte to the right. So don't forget, strides is specified in bytes, not in the number of elements. So in Julia, again, that's different. Okay. Then you can assign to specific elements. I already showed you, so there is nothing special about that. There are no things here. So basically, what you have to keep in mind is we have zero-based indexing. So the first row is 0, not 1. The second column is 1 index, not 2, etc. So that's important. And what happens here under the hood, if you specify an index like this, in Python, it gets implicitly converted into a tuple, and that is being passed into the square bracket operator. So that is something that is quite a nice language feature which is exploited here to give you a nice experience of how things can get indexed. This is much more interesting in C++, unless you have C++23 and your compiler supports it and so on. Okay, so we can also access subarrays using slicing. So you are familiar with slicing if you have a Python background, because I can create a list. Let's say 5, 7, 3, 9, 1. Okay, and if I want a sublist, let's call that L1, I can slice L. I start at the second element. I go up to the third element. Okay, and L1 is going to be 7, 3, and 9. So the second, third, and the fourth element. Okay, no problem there. And of course, we can happily do the same thing in with NumPy. Let's create the array out of L, just for convenience. Okay, square bracket too much. And of course, V is what you would expect, an array with 5, 7, and 1. And now, of course, I can do the same thing. Let's call it V1 and V1. What was it? 1 to 4. Memory serves. Yeah, okay. And you see that V1 is the same thing. Okay, is it the same thing? Let's do an experiment. So basically, let's set the second element of V1 to -3. Okay, you're not going to be surprised. Yeah, and that's exactly where we're going here. Just a second, give me a second and your question will be answered. So as you can see, V1 has changed as you would expect. Now let's have a look at V. And this is something that you might not expect. Because also V has been changed, although I didn't touch it. So essentially that means when I create a slice or a subarray if you want in Python, in the NumPy array, that in fact I'm not creating a copy of it, I'm creating a new view on part of the memory in which the original array is stored. So I can play that same game in with two-dimensional arrays, and I'll do that in a second. But let's first have a look how Python actually works. So if I assign to the second element -3, and I show you L3, no surprises. I show you L, and L is unchanged. So if you slice a list in Python, you get a copy of the elements in that list. If you slice a NumPy array, you get a new view on the elements of the original array. So that is something which is different and something that makes sense, but that you also need to be aware of. Okay, I'm saying this makes sense, but does it make sense according to you? Why would the designers of NumPy have taken this approach? Because of course this is potentially very unexpected. And if you're not aware of it, this may lead to very, very interesting bugs and bugs that are really, really hard to find. So why did they decide to do it this way? Memory saver, maybe. No, could be definitely an argument. But there is one which is even more important. Memory and performance, indeed. Because I already mentioned that if you need to get something from memory and send something to memory, so basically make changes in something that stores in memory, that is really slow compared to numerical computations you can do. So what you try to avoid, if possible, is data movement. Now, by creating a new view on your data, rather than copying it, you potentially gain performance. If you don't need a copy, no copy is made. And that makes sense from a performance perspective. So for those of you who will attend Python for Data Science next week, I will tell you that Pandas data frames do the opposite thing. They are always going to copy a data frame. From their perspective, it also makes sense because you very often use Pandas for exploratory data analysis. So if your data frame was changed all the time when you do manipulations, then you would have to restart your analysis once you notice, oh, that was a very bad decision. You would have to re-evaluate quite a lot of things. And that's something that when you're in an exploratory phase, exploring your data, would slow you down considerably as a user. So the Pandas people have made the exact opposite decision, and again with good reason. Both the NumPy people and the Pandas people looked at the typical use cases of their data structures, be it NumPy arrays, be it Pandas data frames, and decided to do the design or to make design decisions that makes most sense for their particular use cases. Okay, so we can do. We just have to be aware of this. It's a good choice, but we need to be aware of it. And of course, if we want a copy, we can make a copy. It's a decision which we can make. So for instance, v2 would be v14.copy. No. Now, v2 would be, no surprise, the same thing. If we assign to the second element of v2 the value 13, that of course happened, but v in this case is unchanged. Obviously, I made a copy, I'm operating on the copy. So you can always create a copy when you want to, but it's a conscious decision. NumPy is mostly consistent about this, but not always. So if you're in doubt, check the documentation whether what is returned by a function is going to be a view on the original array or a copy of that of elements of that particular array. So always check, but normally you would have a view, not a copy. Okay. So you can select by slicing an entire an entire column by specifying that you want all the rows. So in this particular case, you would get the second column, and that would be 2, 7, 12, etc. Okay, if you want a third row, okay, that's row index 2 and any column. Okay, those are all 1D arrays, so NumPy does not have the notion of a column or a row vector. Everything is just a one-dimensional vector. Okay, you can also play the game with a 2D subarray. So I want to go from the second element up to and including the third. And I do that for both rows and columns. So basically that would be this guy here. And I can assign to that even. So those values would be assigned a 2x2, a 2x2 identity matrix, and you see it here. So you can use slicing to get a different view on on an array, but also to assign to parts of that array. Okay, as I showed you, it's viewing, not copying. Okay. You can also do fancy indexing. So basically we create an array, in this case it's 3 by 3. Notice that I can do the reshape here. So if I have a range, I can reshape my array to whatever I want. And reshaping, by the way, is very cheap. So that does not take any performance. It's just changing the metadata of your array object. So that's really, really fast. So don't hesitate to reshape, it's a cheap operation. So now we can do fancy indexing, for instance, conditional indexing. So I index A by an expression that involves A. So basically this means I look at the elements of A and I check whether they're odd or not. If the element is odd, of course, then the remainder after division by 2 is going to be 1. And this means that I will set all the odd elements of A to 0. So basically that would mean 1, 5, 3, 7, 9 would be replaced by 0 here. So this allows for the very easy masking of your arrays, which is rather nice. Of course, you should realize that this actually creates a 3 by 3 Boolean array. Okay. You can do conditional assignment using the where function. So this works similar. Essentially, you have again a Boolean condition. So in this case, all the positive elements of A will be assigned 1. All the elements that are equal to 0 or smaller are going to be assigned -1. So in this case, we would have a -1 here, here on the diagonal and the off-diagonal elements, and all the others would be 1. Okay, so you can use either conditional indexing or you can use the where. Where can be very convenient because you can specify an alternative as well. But again, you would have a 3 by 3 Boolean array here. So that means that for very large arrays, you have to be a little bit careful if you use fancy indexing. So this conditional assignment or conditional indexing, because it means that under the hood, you are going to create a rather large Boolean array. And that that will take up memory that you might not have taken into account. So remember that this potentially is an issue. Okay, operations on arrays. So adding, subtracting, multiplying, or dividing all elements of an array with the same scalar value is very easy. So that works for all the Python operators, also the power, etc., etc. So basically 3 plus A would add the scalar 3 to each element of A. And indeed, we get this particular array then. So I guess that there are not really surprises here. That would work in most programming languages. The element-wise operators are the exact same. Of course, the shape must match. If I use the addition operator, then I can make the sum of two arrays as the element-wise sum. And the same, this might be confusing, for the multiplication operator, I will do an element-wise multiplication here. So for the MATLAB people, be careful. You don't need to prepend a dot to the operator in order to get the element-wise operation. So the dot star does not exist in Python. Also note that the power operation is double star, not the caret as it is in MATLAB. Okay, so that's something to keep in mind. A asterisk b means the element-wise multiplication of a and b. So that also means that I can do a times b on arrays that are not where the dimensions not match, but that have the same shape. Okay, if I want the matrix product, I have two ways to do that: either the np dot function or the a at b at operator. So that is was introduced in Python 3.5. I don't think there's anyone using an older Python version at the moment, so I would say always use the at operator. We can do that now, so it's convenient. Okay, functions operating on arrays. So we have two arrays, and here's an example of using an empty array. So I have a 500 by 500 array, and I don't initialize any of its arguments. Why? Because here I'm going to assign a value to each of the arguments without using whatever was in that array in the first place. So it would be a waste of time to do a and b zeros, for instance, 500 by 500, because that would mean that I would spend time on filling memory locations with values. That takes time, and I'm never going to use them. So that's why np empty comes in handy for performance. Okay, so I'm iterating over the rows and the columns of I, and I'm assigning to each element ij of A, I'm assigning the square root of the corresponding element bij in B. Okay, there is a void here, and there's a good reason for that. What you should use is, of course, the np square root function, and that operates on entire arrays element-wise. This gives you quite a performance boost. That's a factor of 21. Of course, MATLAB people are really not surprised, because that's the first advice you get when you start learning MATLAB. Don't do do loops. Use the element-wise functions. Use MATLAB functions that operate on entire vectors, entire matrices. So that is the same in MATLAB as in NumPy. You should really use these functions. The performance difference is quite huge. By the way, just as an aside, the numbers probably are not really realistic anymore. The slides are a couple of years old, and it's quite a while since I last timed this. So probably the 21 factor is still okay, but the number of microseconds is probably different by now. It's just to give you an idea of the performance difference. So NumPy has many functions. All the obvious ones like trigonometric, hypertrigonometric, exponential, logarithm, square root, whatever, very many. Check the documentation. Probably what you need is going to be there. And then there are, of course, a number of matrix-related functions, such as the trace of a matrix and the transpose of a matrix, and so on. Okay, there is a little bit of linear algebra in there as well, but not that much. Is there a question? Because someone raised his or her hand. Okay. Yeah, okay. I'm not sure that you can actually remove those pop-ups. I don't know whether there is that sort of functionality in Blackboard. Okay, so a little bit of linear algebra. There are some operations, for instance, matrix power. Again, MATLAB people, be aware, you need to use the matrix power function, because A star star 3 means element-wise power operation. So that's something entirely different. Don't get confused here. That's a dangerous one. The inverse, there's a function for that as well. So, okay. Excellent. Then there is a determinant and so on. Eigenvalues and eigenvectors you can also compute. So all of this is in NumPy, but there is a lot more linear algebra in SciPy, and that's the next topic. Okay, references versus copies, I already told you, so there are no surprises here. That's what I showed you in the notebook, so I'm going to skip that. I've told you. Let's talk a little bit about I/O. So let's read a text file with a textual representation of 10 to the 9th 64-bit floats. Okay, so that's a billion numbers. Okay, we can do that with a function which is called from text, and that would take 57 minutes. And interestingly, you would need 44 gigabytes of RAM to do that. Okay, that's a little suspicious because a billion 64-bit floats should actually take 8 gigabytes of RAM, not 44. And also, reading needing an hour to read a billion floating point values seems also a bit excessive. There is another function which is called from file, and this you can use either to read textual data or binary data. If you wanted to read textual data, you need to specify a separator, which is basically the row separator. Okay, and this only takes less than 5 minutes. And as I would expect and hope, it only uses 8 gigabytes of RAM. So I noticed this and I thought, okay, this is very bizarre. So I looked at the implementation and it turns out that from text is actually first creating a list of lists and then turn that into a NumPy array. That explains on the one hand why it takes so long, because creating a list of that size is, well, time consuming. So basically this is a factor of 12 in difference. So yeah, be a bit careful. There is a lot of functions in NumPy and some of them are not necessarily optimal. So check the documentation carefully when you have alternatives, what the reason is that there are alternatives. So personally, I think that the person who wrote from text, yeah, should be executed, but okay. So this is reading textual data, but we can do much better. So if we would have a binary file, which is not human readable, with the same number of floating point values, as you can see, that only takes 8 seconds. We can use the same from file function, can also read binary data. So that is a speed up of a factor of 35. So I/O, as you may or may not have realized, can also take up a lot of time and can also be quite time consuming. And maybe it's a good idea to look into how to optimize that as well. So binary files are not necessarily nice because you can't read them and you need to know what's in there. So a very good alternative there is HDF5. And that actually is a binary file format. It gives you excellent performance, but it also contains metadata so that you at least know what's in there without trying to figuring it out manually. So we can talk about HDF5 later in this training. Okay, so for the MATLAB people, there is something called NP matrix, and the nice thing, it overloads the star and the double star operators. So you could do matrix multiplication with A times B and matrix power with A to the power 3. But and the result is always a 2D matrix, so that's very similar to what MATLAB would do, but I would say don't use it. It is going to be confusing. The typical NumPy user is not doing this, and using other libraries will get very tedious. So I would say don't do that. That's the bottom line here. I'm just pointing it out because as a MATLAB user you might be tempted, but really don't. Really bad idea. Don't do it. Okay. So if you think, okay, would NumPy be something for me if I'm a MATLAB user? This is a fairly old article which compares MATLAB and NumPy. I'm not a MATLAB fan, so I thought, okay, I'm not going to judge this. So I asked one of my colleagues who teaches MATLAB trainings and is also very familiar with MATLAB. what he thought about it, and he thought it was a fair comparison. Really a fairly written article, which does not favor either NumPy or Matplotlib, but just gives you a very balanced comparison between the two, talking about strengths of one language versus those of another. So it's a good read if you're considering NumPy as an alternative for Matlab. Okay, this is what I wanted to tell you about NumPy. Are there any questions about this? I've talked a little bit about performance issues. So if you are concerned with performance, you should consider attending Python for HPC. There I talk a bit more about performance also with NumPy and so on, because there are dragons there, which I didn't mention now, but which I would mention in that training. Okay, high time for a break. So let's break and then talk a little bit about SciPy. 10 minutes break, something should be okay. So let's make that break too. Let's make it 11:05. That should give you, well, it gives you 12 minutes, but okay, we have been talking for quite a while, so all right. So see you later after the break. If there are any questions, feel free to type them in the chat. I will get some more tea, but I'll be back and discuss questions afterwards. Okay. See you in 10 minutes. Okay, let's continue. I'll share my screen again. I hope. Okay, go. You're right. It's always a bit adventurous because from time to time it happens that Google Chrome goes down and then. All right. So, yeah, let me make the chat visible. All right. So, any questions about NumPy? Meanwhile, not really. Okay, so another very useful library is SciPy, and it builds in part on top of NumPy. So basically, it adds quite a number of interesting things. One of the things in which it complements NumPy is in fact in linear algebra. So it defines quite a lot of linear algebra algorithms on dense matrices, and those dense matrices are of course NumPy arrays. However, it also supports sparse linear algebra, so sparse representations of arrays, of matrices and vectors, which of course NumPy as such does not support. And then there is also modules for solving ordinary differential equations, numerical integration, optimization, interpolation, signal processing, statistics, more statistics than in NP than in NumPy. And in fact, typically all the statistics I personally need, but I'm not a statistician, I just use statistics from time to time. So don't take that as saying that this will replace R, not at all. But for mere mortals, with respect to statistics, well, I will find quite a lot. Now, a lot of mathematical functions and constants, so mathematical and physical constants. Often you see import SciPy as SP. Again, it's a convention, but I don't think it's as strict as the one for NumPy. Okay. You can also import sub-packages directly, like for instance the linear algebra sub-package, so that you can use things like SVD and so on. So there are many matrix decomposition algorithms, like for instance singular value decomposition. And again, the MATLAB people will recognize this. So we import SciPy linalg, and then we can do SP linalg SVD on an array. Okay, we get the U and the V matrices. So those those are actual matrices, two-dimensional arrays, and S is in theory a diagonal matrix, but what you get is just a vector, a one-dimensional array with the diagonal elements, which are your values, your singular values. Okay, so you can always use NP-diag to create a two-dimensional array out of a one-dimensional vector. So that would give you the corresponding diagonal matrix with the elements of S on the diagonal. So that is very easy. And then, of course, you can reconstruct the original matrix by multiplying U, S, and V. And then you can compare. And as you can see, we have the difference is of the order of 10 to the minus 16. This is double precision, so that's indeed what you would expect by a trivial round of errors. So as you can see, this is quite simple, and the SVD function behaves very much like its counterpart in MATLAB. Okay, and of course, this is going to be fast, because under the hood, the SVD function is going to use LAPACK. LAPACK is another, let's say, low-level linear algebra module, linear algebra package, basically. And that under the hood in turn uses BLAS. So if you have a proper installation of Python, either because you're using a module on VSC infrastructure or you're bit writing with installing your own version, then actually you will get quite reasonable performance here. Okay, another thing which is common is linear regression. So we've got a data file that contains comma-separated values. So each row represents an X and a Y value. We have many of such rows. So we first read the data, and we can use gen from text for that. So in this case, of course, we need to specify a number of things. The delimiter, for instance, is a comma, because gen from text by default expects spaces as delimiters. So we can override that by setting the delimiter. We also can include an optional argument names is true, and that basically assumes that the first row, that the first line is actually going to contain the name of the columns. And then we also explicitly specify the D type for both columns, and we want it to be float64, and of course the name of the file, and that goes into data. Now, since names is true, we can do something interesting. Data is still going to be a NumPy array, that doesn't change, but there's something interesting here. We can index data by column name now, because of this names is true. So basically this looks a little bit as if it were a pandas data frame. So in that respect, NumPy arrays can have named columns. So that can sometimes be convenient. So we want to do linear regression. Linear regression is in the stats subpackage of SciPy. So we import SciPy stats, and then we can do lin regress, the x values, the y values, and we get the slope, the intersect, r, and two other measures for the quality of fit back from the lin regress function. So quite straightforward, nothing much to it. Yet another example is optimization. So basically we want to minimize this particular function in two arguments. So essentially we want to know what the X and Y values are that will yield the minimum of this particular function. This is a somewhat tricky one, because if you plot it in 3 dimensions, it would be like a Mexican hat, but it is a little bit tilted due to this last term here, this 0.1.x, that tilts it a little bit in the X direction. So basically that means that there will be a minimum at one end of the hat, and there will be a saddle point at the other end. And then, of course, if you're nasty like me, you put the initial point on the saddle point just to make life a little more interesting. But that's the detail. Okay, so the first thing you need to do then is to define your function, and that's very easy. It takes an array, well, an array of values as an argument, but for convenience, we just assign that to x and y. We could just use x0 and x1, but if we think in mathematical terms, personally, I find it much more convenient to just say, okay, I'm going to use tuple unpacking here, and I'm going to use the names of the variables which I actually have in my function. So we return this function. Very straightforward. Okay, then it helps for some optimization methods to also define the gradient. And then, of course, that means that we have partial derivative of f to x, partial derivative of f with respect to y. And this we return as a NumPy array. So we first compute the x partial derivative, the y partial derivative, and return that as a NumPy array. Very straightforward again. That's just a little bit of calculus. Okay. So then we can actually compute the minimum. So this lives in the optimize module of SciPy. And we first initialize, well, we first set the initial values of x and y. And in this case, I'm putting it to 1 and 0, 0.1. Okay. And then we can use any of the optimization algorithms. So in this case, I'm using fmin CG, which means conjugate gradient, and I specify the function to minimize. I specify the initial guess for where the minimum is, and I specify f prime, which is basically the gradient. And then I set display to false. So display to false means only give me the results. The default value is displayed true, and then for each iteration of this minimization algorithm, it will actually give me output so that I can see whether my algorithm converges and so on. So for debugging purposes, that's quite nice. In production, you might want to switch it off. I just mentioned it that you can switch it off because by default it's on. Okay. So that would give you a one-dimensional array with two elements, x opt, and that would be the minimum, well, the x and y values that minimize the function f. There are many methods. So I mentioned the conjugate gradient method. There's also Powell's method, the FGS, Newton conjugate gradient, and so on. There are quite a few. So just check the documentation for whatever makes most sense in your case. Okay. As I mentioned, ordinary differential equations, no problem. Basically, you can solve any order differential equation. This is a second order differential equation, but not directly. You have to rewrite this as a set of first order differential equations. Okay, so in this case, we would introduce omega as the derivative of theta. And of course, physicists among you will have recognized this differential equation as describing a harmonic oscillator subject to damping and subject to an external force with amplitude Fd and frequency omega d. So basically, we rewrite our second order differential equation into two first order differential equations, and then we can define a function that encodes the right-hand side of these equations. So again, the signature of this is that the first argument must be the time. The second argument is going to be an array that contains the current values of all my functions. So in this case of theta and omega. And then I can have any number of parameters. In this case, the gravitational acceleration on Earth, the length of my pendulum, then the damping factor Q, amplitude of driving force Fd, and the frequency of the driving force, omega d, and so on. So again, I'm unpacking y into theta and omega because that makes my formula more readable. So the right-hand side of the first equation is just omega. The right-hand side of the second equation is the whole expression here. So basically, it's time dependent. So yeah. Okay, then just as for the optimization, we define the gradient. We can, in this case, define the Jacobian. So basically, the Jacobian would be the right-hand side of the first equation, partially derivative with respect to the functions, so theta and omega. Second equation with respect, etc. So essentially, this boils down to a similar function. It also takes time, the time as the first argument, then an array containing the current values of the unknown functions, then all the parameters and so on. And of course, this is fairly straightforward. If we derive the right-hand side of the first equation with respect to theta, that's 0. With respect to omega, it's 1. And here, essentially, it's also pretty straightforward. If we derive with respect to theta, we get minus g divided by L. If we derive with respect to omega, then we just have minus q. And of course, the term which represents the driving force does not depend on either theta or omega, so it doesn't play any role in the Jacobian. And of course, that also means that time is not relevant. Just for convenience, I've put the same parameters here, although some of them are not needed. We need G, we need L, we need Q. We would actually not need FD and omega D because they don't enter this particular Jacobian, but just for symmetry with the previous function, I have included them anyway. So basically we turn this as a list of lists, no problem. And then we can define our solver. So for that we use the ODE function in SciPy integrate. And now I'm importing from SciPy integrate, so I can directly use ODE without any qualifiers. And I need to specify the right-hand sides of the equation, optionally the Jacobian. And then I set the integrator, in this case, to Dopri 5, which is a Hongakuta variant with a 5-degree stencil, basically. Then we set the initial values, so theta 0, omega 0, and t0. Note that initial values of the functions are in fact given as a list, and then we have an additional the additional value, which is the integration variable t0. And we set the parameters for func and the parameters for Jacobian. These are the G, the L, the Q, FD, omega D, and so on. Okay, so this sets the stage, and then we can start our solver. So we integrate step by step, as long as the solver is successful. And of course, as long as the time is less than the maximum time I want to integrate to. So obviously the time starts at t0 and it runs up to tmax. So in each step we do an integrate and we specify the next time step. So the current time plus some delta t, and then we print the current values of the time and of our two functions, theta, which would be y0, and omega, which would be y1. So quite straightforward. You can print them, you can store those in arrays or in NumPy arrays, whatever. Of course, note some solvers will have steppers that do non-uniform steps. So that's why actually you pass in the current time plus your delta t. So it does not mean that all times will be always equally spaced. That depends on the stepper which is used by the solver which you're using under the hood and that you specify here. So the documentation contains the list of solvers which are available. I think in total there's something like 5, but they're in a way families of solvers. So there are solvers that can automatically switch depending on whether you have a stiff system or a non-stiff system. So basically, it's a reasonably powerful library. Okay, so quite convenient. An example from signal processing. So this actually comes from a real-world problem. A number of biologists wanted to count the number of nightingales in a particular area. But of course, counting nightingales is not so easy because they're active at night. And they thought, well, okay, can we put a number of microphones in the area and then try and identify individual birds and see whether we can count them that way. So, of course, there is a lot of noise involved because, yeah, silence in Belgium is something that does not happen anymore. There's always somewhere a road nearby and you will have noise. So it was interesting to see how far you can go with noise reduction without actually destroying also part of the finer details of the bird song, which then would make identifying individual birds a lot more difficult. So I decided to experiment a little bit, and I had sound files encoded as WAV, and that's essentially a fairly straightforward way to encode sound. You sample the sound at regular time intervals, and that's determined by the sample rate, and that's part of your WAV file. It's information that is metadata in that file format, and then essentially you have, for each time point, you have a value which is between 0 and 255. Okay, so one of the nice things about SciPy is that it also contains its I/O module with a lot of readers and writers for scientific data. One of them is indeed WAV, and you have a reader and a writer for WAV. So you provide a file name, and what you get is the sample rate, which is important information because otherwise you can't really interpret the signal, and then the signal itself. Okay, so of course, if I'm interested in filtering noise, removing noise, I need to know about the frequency spectrum of the signal. And for that, of course, you're using a fast Fourier transform in order to get the power spectrum out of the signal. So we determine the length of the signal, we get the frequency, and that would be the sample rate times the well, we get the frequency spectrum essentially. So these are the values of the frequency. So it would be sample rate divided by n, and then times each time a number between 0 and n, non-inclusive, where that's the length. Okay, we can do a fast Fourier transform. Either we can use the NumPy one or the SciPy one. For no reason, I decided to use the SciPy one, and we apply that to signal, and we normalize by the length of the signal. So that gives us y. Okay, and this is essentially what we get. This is the original signal. This is the power spectrum. So as you can see, a lot is going on around 3000 Hertz, and that is likely the birdsong, including here the very high frequencies. This is probably the next harmonic. Okay, but there is also some stuff going on here at very low frequencies, around 100, 200, something like that. Okay, I could try to play this, but that's probably not going to help very much, so let's not do that. But basically, it's quite a noisy signal. You can see it here. So this is a chirp of the bird. That's another chirp of the bird. And in between, you see noisy stuff. So this is basically this frequency here. So that's a road in the background, traffic on the road. Okay, now, to be honest, and for those of you who are biologists or who know anything about birds, the bird call here is in fact not a nightingale. It's another bird. I think it's a blackbird. I'm not quite sure. Don't remember what I took, or it might be a robin. I don't know. But anyway, it's definitely not a nightingale. But okay, it was just for testing purposes, so nobody cares. All right, so what I want is to get rid of these low frequencies. So what I need is a high pass filter. Okay, so I'm going to import the signal processing module of SciPy, and I'm going to use an IIR filter. So that's basically a filter which will suppress, in this particular case, it will suppress low frequencies, it will let pass high frequencies as well as possible. So that's what I'm specifying here. The B type is the filter type I want, and I want a high pass. High frequency should pass, low frequencies should be cut off. Okay, you need to specify a number of things in addition to configure this. So basically 17 here is the order of the polynomials that are used. This is the fraction of the Nyquist frequency. So basically, you can compute the Nyquist frequency, and you want a certain cutoff that determines what is considered low frequency, so what should go, and high frequencies, so what should pass. So this cutoff is pretty important to get right. Then this is not an analog signal. We don't care. what we want to use in order to construct our filter is Chebyshev polynomials, a particular family of polynomials which are orthogonal and which you can use in order to decompose other functions in or use to compose any function. And I use 17th order, which is a bit too much, but okay. So basically, this is the order of the filter, and the filter is going to be consisting of Chebyshev polynomials. And then I also specify that I want minimum attenuation. So basically, I want a filter that tries to leave the high frequencies as unchanged as possible. So that's essentially the idea. Okay, so I can apply the filter to my data, but I first need to convert it to uint8. And sorry, I was a little bit wrong when I described the WAV file format. In fact, it's int8. So it contains negative numbers, but we want positive numbers here, so we convert our signal to uint8, and that's our base. So then we apply the filter to the signal, okay, and then when we have our filter signal, we add the base to that. And basically, that makes sure that we get again the right values. So as you can see, this is just a few lines of code. And basically, that will give us, what is A and B? This I forgot. A and B is the result, sorry, is the result of our filter. So basically, these are our forward and backward filters, which we put in. Okay. And then we have to write the signal to a WAV file because we actually want to hear it. And of course, we also want the power spectrum. Okay. When I wrote that code, and meanwhile, it's like 8 years ago, at least, I did understand what I was doing, although it was quite a while since I had a course on signal processing back in the 80s of last century, so quite a while ago. Since that time, I had not done anything with signal processing. Typically, I don't do much signal processing in real life, so I had to read up. And why am I telling you this? Because I really understood what this was doing. Also, the IRR filter, how it worked. By now, honestly, I've totally forgotten. It's too long ago. But I understood the whole thing. And I got everything working, including understanding what I was doing in 1.5 hours, which is, if you bother to read up and understand what you're doing, fairly fast. And this is what you get. So as you can see, the noise is gone here. And also, if you look at the power spectrum, indeed, that peak around, well, between 100 and 200 is indeed also gone. And you get much, of course, much clearer signal. And that would form the basis of trying to identify distinct birds. Why did I mention the time? Because that's one of the very nice features of a number of Python libraries, including SciPy. So they typically contain references to the algorithms that are implemented. And so you can look at the documentation and see a reference to something that gives you more information about that algorithm and read up on it, which is always a good idea, rather than applying algorithms blindly and having no clue what's going on under the hood. Okay, any questions about NumPy? So of course there is much more. I haven't talked about sparse matrices. I haven't talked about interpolation. I didn't mention integration and so on. So basically, there is of course a lot more. You can talk like 2 days about only SciPy. So this is just, the aim is just to give you some idea of how it works, that it's easy to use, and that it's also fairly easy to understand the algorithms that you're actually using under the hood. Any questions about this? Okay. So an important part of scientific computing is visualization, and your primary visualization library is in a way going to be matplotlib. Should you use it? No, not necessarily. For certain purposes, there are other libraries which are much better suited. For instance, if you're into statistics, I suggest you don't use matplotlib, but rather Seaborn. I will be talking about Seaborn in Python for data science next week. But yeah, that's, in my opinion, mostly for statistics people. You can use it as a non-statistician, obviously, but its biggest added value is for plots you typically make when you do statistics. Matplotlib is your primitive go-to without, well, with a lot of features which are not necessarily accessible. But making simple plots with matplotlib is very simple. Doing sophisticated things gets a bit more complicated. Okay, so you can do scatter plots, line plots, bar plots, histograms, and so on, heat maps, 3D surface plots, etc. So basically any type of plot. You can manipulate anything you want, so essentially it's extremely customizable. Although it might not be easy to do so, you can. It also supports LaTeX labels and annotation, which is kind of nice if you want to make graphics to include in scientific articles. May not be good enough, but for some cases you can get away with this. And then of course you can plot to screen to various file formats, depending on what you have installed on your system, but okay, that's an aside. So again, you can talk like 2 days about matplotlib, all kinds of nasty things you can do, animation and whatnot. I'm only going to talk about fairly basic usage, not going into lots of details. Okay, so again, there is a convention. Typically, you import matplotlib.pyplot as PLT. Okay, so let's start with a simple line plot. Let's create some data. I've got X, and that's a linspace numpy array between 0 and 20, and I've got 500 points. Okay, then I'm computing the exponent of that. Basically, you will recognize this as the solution to our differential equation with damping. In this case, the damping factor would be mu, but without a driving force. So essentially, this is an attenuated cosine. Okay, so making a plot is very easy. PLT plot, y versus x, done. And you can show the plot, and here it is. Okay, I can do that in a Jupyter notebook. So let's import matplotlib.pyplot as PLT. Okay, and then x is np.linspace and 0, 20, 101 points, and y is np square root of x. I'm going to make it a little simpler here, and I can just do plot, and it will appear in line, and I've got my function. Okay, if you don't want this, because actually PLT plot returns an object, if you don't want that shown in your notebook, just put a semicolon there, and then the output of that command is suppressed. This is a little bit like MATLAB. Okay, so quite straightforward to do, no problem. Okay, so you can save the plot with the savefig function, so that will save the last figure, and you specify the file name. Depending on the extension, it will do the right thing. So if you do something.png, you will end up with a PNG file, with a JPEG file, with a PDF file, if the necessary libraries are installed. So basically, that's quite straightforward. Okay, so you can start adding annotation. So you can specify an X label. You can specify a Y label. It's just PLT X label, PLT Y label. And then you can use a LaTeX expression. You can specify the font size and so on. Basically here I would have the Greek letter theta. Notice I use \r here. I use an R string here because \t in a normal string actually has a meaning. That's a tab character. So if I want a literal backslash, I would either have to use \t, or I can use an R string, and then the backslash loses its special meaning. So R strings are very useful in Matplotlib because of LaTeX being full of backslashes, and also in regular expressions. Okay, so you can also add annotation. You just specify the coordinates where a specific text item should appear. And again, you can control font size. So the coordinates are with respect to the axis of your plot. So there are no two coordinate systems as in many plotting applications. There's just one coordinate system, and that's the one defined by your axis. So that simplifies lives a little bit, but it might be some getting used to. And then if we do that, you see that indeed we get a t, which is a variable and hence print in italics. And we've got our theta t here as well. And we've got our formula, which is essentially the differential equation that describes this particular function. Okay. So I'm not extremely happy with how this formula is rendered. It's not really well done. So if you would do that in the proper LaTeX document, formatted by the LaTeX processor and so on, you would get nicer output. So that's what I mean. You can get something that is close to publication quality if you don't do this kind of complicated formulas as annotation. Okay, so constructing a plot is basically gradually enriching it. You can do this step by step, interactively. So I could say, okay, I want a label here. So essentially PLT X label, and I want X, and I want PLT Y label, and I want that to be in this case strt X. Okay. And then you see that indeed I get square root of X here and X there, etc., etc. So I can do that step by step, and that is convenient. If you're working in a notebook, then you can build up your graph as you want. Okay, I can have multiple functions on a line plot, so I create additional y values, one for the exponential of minus mu x, and the other for minus the exponent of minus mu x. So basically that means I want the envelope of the curve. So I just do additional PLT plots, and as you can see, here is my dotted line and my other dotted line. I can specify that I want a dotted line by using the column here. That means a dotted line. If I would have a dash, that would mean a dashed line, and so on. There are several things that you can use. I also specify the alpha value, and the alpha value means transparency. So 1 is totally opaque, while 0 is totally transparent. So I do this because otherwise this would look ugly. It would be a very prominent dotted line, and I want that to be a bit more subtle. So that's why I choose a transparency which is, well, an alpha value which is less than 1, but not too low because otherwise you don't see it. And then as color, I specify something. I specify line width, which is a bit less than the default, which is 1. So basically you can play with this in order to improve how your plot will look at the end of the day. Okay, so this would be the complete plot. these were not in, I used less than 500 points, so that's why it's a bit jagged. This is with more points, probably 501 points or something, which gives me a pretty smooth plot. Okay, let's close this. Let's turn to histograms. So I've got some data, and it lives in a data.txt file. And in this case, I'm using yet another function to read data, which is load text. Okay, so we have from text, we have from file, we have gen from text, and we have load text. Why? I have no idea. It's probably there for historic reasons, but whatever. Okay, I also specified that I want 50 bins. It's a histogram, so basically I'm going to bin things. So PLT hist, specify the values, the number of bins, whether it's normed or not. And in this case, I want it normed. And I want to set the color to red. And again, I'm playing a little bit with the alpha value. And I set some X and Y labels. And as you can see, this is the distribution of my values in the file. Okay, why do I set the alpha value? If I don't set it, then I will get a huge red block, which really does look ugly. So again, this alpha value just to make things look a little bit nicer. Okay, so actually I can combine histogram and the line plot. So I'm guessing that this is a gamma distribution. Okay, so again, in the stats package of SciPy, there are several distributions, among them the gamma distribution, and this is the PDF of this particular distribution. So I specify X, and X is a linspace array, and 2 is the parameter of the gamma distribution, and scale is the parameter of the gamma distribution. So 2 relates to the position of the maximum, scale relates to the width of the gamma distribution. Okay, and I plot that with a larger than normal line width, with 2 rather than 1, and the color is black. Okay, and then you get something like this, and you see that indeed my assumption or my guess that this is a gamma distribution is in fact quite plausible, because this matches quite nicely. And of course I know, because I can also use the gamma distribution to sample from, and that's exactly what I did to create my data set. So of course in advance I knew the 2 and I knew the 3, because those were the numbers I'd chosen to create the data in the first place. Okay, so we use a lot of stuff here. We use NumPy, SciPy, the stats package of SciPy to be precise, and then of course also Matplotlib. Okay. Personally, I like heat maps as a visualization tool, so you can also do that quite easily. I create some data and I'm going to use a function, and that function is just going to add essentially 2 Gaussian functions. So basically, that's what's happening here. They have different frequencies, and what am I doing here? That is weird. Ah, no, I'm not doing that. Sorry. So this is 1. So it takes an x and a y and some values. And then to create the data, I'm going to use this function, but I'm going to use mesh grid. So these are my x coordinates, these are my y coordinates. I'm turning that into 2 matrices using NP mesh grid. And that's very familiar to Matplotlib people. They have that function as well. And then I can pass in x and y as arguments to f. Note all of these are NumPy functions, so they operate on entire arrays. I set some values, and I do that twice. I add 2 together. That gives me z. Z is a 2-dimensional array with x and y coordinates, well, corresponding to x and y coordinates given here. And then I can do an IM show offset. IMShow is in fact image show, but basically it shows you a two-dimensional matrix. I set some extent, so the X and the Y boundaries, and I want the grid to be plotted. And this is what I get. And this is really ugly, but you recognize that there are two functions here. Those are the two maxima. Red is large, blue is small. So what I would suggest is to explore color maps, because this is really ugly, but it helps to interpret data. And I would certainly point you to Brewer schemes. There is a reference in the slides, and that helps you to pick. Well, Brewer schemes are designed by a researcher called Brewer. Don't remember her first name, but she designed some color schemes specific to certain data sets or certain visualizations. And it's definitely worth checking that out. There is an online application that allows you to pick the most appropriate color scheme, so the most appropriate Brewer scheme for the data you want to visualize. And you can also indicate that, for instance, you want to take into account some visual impairments like color blindness and so on, so that actually the colors are chosen in such a way that for people with visual impairments, it's still possible to easily interpret your plots. So you're strongly encouraged to have a look at that. Okay, so here's an example of using a color scheme, but in this particular case with a 3D plot. I'm not going into the details here. I typically very much dislike 3D plots. It's not for me. But again, you can specify a color bar, and this you can also do for heat maps. So that's not particularly interesting. The interesting part here is that you can specify a color map. You can also do that for the heat map. And in this case, I choose cool warm as color map. And then you see the high values are in bright red, or in saturated red. The very low values are in saturated blue, and everything in the middle is grayish. So this is a very nice color scheme if you are interested in outliers, because large values will be red. They'll really grab your attention. Very low values will be blue. They will grab your attention. Anything in the middle you don't care about, because that's by definition not an outlier. And that will be grayish. So everything that's an outlier will stand out very clearly. So that's an example of using a proper color scheme actually helps you interpret your data much more easily. So as I mentioned, Color Brewer is that particular website which allows you to, depending on what your data looks like, choose an appropriate Brewer scheme. Coblis is also quite interesting because it allows you to simulate what people with various types of color blindness actually see. So you can just upload an image and it will be converted in such a way that for people without that impairment, it will actually seem, will actually be rendered as people with that particular visual impairment would actually see it. So that's actually nice to experiment with. Personally, I don't suffer from color blindness too much, a little bit, but for me it was quite interesting to experiment a little bit with it and to see which color schemes work and which don't work. And I had quite a lot of discussion with certain researchers during the pandemic because they really insisted on a color scheme that included green and red. And I told them, yeah, that's nice, but people with color blindness are going to see that as gray and gray. So your plot conveys zero information. Yeah, that was an interesting discussion. Let's put it that way. I didn't win, but I was right anyway. So there is also this plot, this web page, and that lists an overview of many different visualization libraries in Python, and especially, well, no, let's rephrase that. It shows you a list of visualizations in Python and the Python libraries with which you can do them most easily. So that's also quite useful to browse to get an overview of which particular visualization library to use. Okay, that was what I wanted to tell you about Matplotlib. Again, you can talk like a day about Matplotlib, do special things with it, create animations with it, etc., etc. For instance, I've used Matplotlib in order to visualize the Towers of Hanoi algorithm, for instance. So there are many things you can do which are cute. It's a very powerful library, but it's quite low level. You need to write a lot of code in order to get something done, which is much easier with, for instance, Seaborn, if you're into statistics, or if you want interactive plots, there is Bokeh. There is, what's the other thing called? Something with an A. I don't quite remember. So those are also very interesting libraries. I'm not going into them here. I think I will, well, maybe Bokeh is here, but I don't know whether I'm going to talk about it due to time constraints. Okay, any questions about visualization? Not really. Okay, let's have a look at the section overview. So in the slides are 4 additional chapters. I can't talk about all of them because there's only an hour left, so we will have to make some choices. The chapter now on screen is, or the section now on screen is SymPy, and that is symbolic computations with Python. So symbolic computations means you define a function, you can compute the derivative of that function, you define or the integral of that function, you can solve sets of equations with parameters such as a and b, etc., etc., and you get the solutions in terms of a and b. So this can be very useful. For instance, we've seen an example, well, we've seen several examples where we had to compute by hand the gradient of a function in order to optimize it, or the Jacobian of a set of differential equations in order to integrate that set of equations. So this we could have done very easily using SymPy. So I consider it quite useful. Also for dealing with non-trivial theoretical, well, analytic work, it's also quite useful. Then another section is about HDF5. So as I mentioned, that's a binary file format, but it allows for annotation, and it is self-documenting in the sense that the data in it, you can retrieve which type it is, etc., etc. So you know what's in a file, even if it comes from somewhere in the world. It's very easy to check what it looks like and what kind of data you can expect. You can also annotate it with, for instance, units. You can say, okay, this particular data set is in meters rather than feet, which may make sure that your Mars lander doesn't crash because, well, meters and feet got confused. It's also nowadays very much used in machine learning. So most machine learning frameworks that I'm aware of will actually use HDF5 to store snapshots of or checkpoints of their models while they're training, and also trained models are typically stored as HDF5 files. A very nice feature of HDF5 is that you can also do parallel I/O, given that you have a parallel file system. Then there is Bokeh. Bokeh is a plotting library, which allows to quite easily create interactive plots. So plots where you can zoom in, zoom out, pan, select certain data, etc., etc. The last chapter is about scikit-image and OpenCV. So that's basically a little bit, not that much, about image processing and also video processing. Okay, I'm going to launch a poll, and you can indicate your favorite, and we will do some of them. So maybe, well, 2 at least, maybe 3, depending on what you choose. Unfortunately, I can't predict because, okay. What would you like? And then we have Senpai, we have HDF5, we have Bokeh, and we have image and video processing, and we have X-arrays. And I'll tell you what X-arrays are. I don't have slides on them, but I do have a notebook. So basically, X-arrays is sort of a mixture between NumPy arrays and pandas data frames, in the sense that you can do a number of operations which you would normally do on pandas data frames. You can do those on X-arrays. So it's kind of the pandas for pure numerical data. In a way, scientific data, I would say, scientific in the sense of, don't get me wrong, social sciences are also science, but in the sense of let's say the physics data, the chemistry data, and so on, you would be inclined to use X-arrays maybe more than pandas, because they are n-dimensional arrays, and you can index them by coordinates, and you can interpolate and so on. So they're pretty cute. Okay, so let's start the poll, and you can indicate what you would prefer. Okay, so HDF5 is a clear winner, followed by Bokeh, and image and video processing. X-arrays and SymPy are not that popular. Okay, so let's start with HDF5, and then Bokeh, and then image processing. All right. I think we can do all 3. That should most likely work. But let's start with HDF5. That's the most popular, and then it's a toss-up between Bokeh and image and video processing. Okay, so let's go to HDF5. All right. Okay, just a second. Something in the chat. Yeah, sure. Everything else is available on GitHub. For instance, the notebook on X-arrays is on GitHub. There's quite some text in it, so it should be quite easy to do it by yourself. Similar for SymPy, there's a lot of material on SymPy. Also some rather non-trivial things where you actually abuse SymPy a little bit to solve puzzles and so on. So there is quite a lot. And maybe, I don't remember where they are. There are also some interesting notebooks, for instance, about Lagrangian mechanics with SymPy, doing the double pendulum differential equations. Well, get them from the Hamiltonian and so on, or from the Lagrangian, not Hamiltonian, I think. No, it was the Lagrangian. So basically, that's also somewhere. I'm not quite sure it's in this repository. Okay, so let's talk about HDF5 first. And basically, that stands for hierarchical data format, and 5 is the particular version. which you're currently using. So there was an HDF4. I've never known an HDF3 or whatever, so that's really, really old. Normally, you should only have HDF5. Okay, so the selling point is that it is a system, operating system, programming language independent to store data. So that's a very interesting promise. You might ask, okay, why system independent? Well, basically there used to be two families of CPUs, and they would encode floating point values differently. And that's what the system means. But as far as I know, at the moment, there's only a single way of encoding floating point numbers. So that kind of went away. But operating system and programming language independent is still quite interesting. Okay, so we have an abstract data model. At the top level, you have a file, so the HDF5 file. Inside of HDF5 files, you can but need not, but you can have groups. In groups, you have data sets, or in groups, you can have other groups. And you have a data set as a data type, and data sets also have attributes. Groups can also have attributes. A file can have attributes, I think. Not sure. We'll see. Okay, so you can actually compare that to a typical file system. So a file system or a file in HDF5 looks a little bit like a file system. A group is similar to a directory. A data set is like a file, and data type and attribute would be metadata of a file or of a directory. So that's more or less the correspondence, the conceptual correspondence between, on the one hand, an HDF5 file, and on the other hand, your typical Linux or Windows file system. So actually, you can kind of do comments in the data file itself. So basically, you can make the data file self-contained in the sense that the data type of your data, all the attributes of your data are in fact automatically part of the file. And if you like, you can annotate by adding attributes, like for instance, I mentioned the units which are specifying the data set. Okay, so that's the abstract data model. And then you have a storage model. So basically, data can be stored in a data set as n-dimensional arrays. It can, and an n-dimensional array is described by, on the one hand, a data space, which is a layout of the data, the rank and the dimensions. That's very reminiscent of your NumPy array shape. So this is essentially the shape of the array. Then the data type. So that would be the D type of your NumPy array. And that's, of course, the type of a single data element. So your data type can be atomic, so an integer or a float, a string, a time. It can also be opaque. So you can create arrays that consist of images, JPEG images, for instance. And that would be an opaque element. This could be useful, for instance, in biomedical image applications, where you say, okay, I'm slicing. If I have fMRI, I have several slices of images, and I store those in an array. Okay, you also have composite types, like a compound, that's like a struct or a tuple in other programming languages, or in programming languages. You've got an enumeration, so that's useful for categorical data. You have an array, and things can also be variable length. Okay, so the data layout and the type description are part of an HDF5 file. So it is self-documenting and it allows for discovery. If you just give me any HDF5 file and you don't give me any explanation, I can still figure out what's in there. I can still figure out all the types. I can still figure out all the shapes of the data sets which are in there. So that makes it quite powerful. What is also a very nice feature is that you can do partial read and writes. So essentially, you can compare that to Python slicing. In HDF5 parlance, it's called hyperslaps. So a hyperslap is essentially just a slice. Okay, then we have the storage model. You have several options. So you can do filtering. Essentially, you can automatically compress an HDF5 file. Now, of course, if you do that, you must realize that writing a compressed file is slower than writing a non-compressed file. Reading a compressed file is slower than reading a non-compressed file. So yeah, you can do that automatically, but it comes at a cost. Fairly straightforward. What you can also include is error detection. So that means if a bit gets flipped, you'll know. Which bits you flipped, nobody knows. So this is error detection rather than error correction. I have, in practice, never seen one of them used. So there are certainly use cases, but I haven't encountered them. Then datasets can be extended. So if you have an n-dimensional array, you can, in one dimension, keep on adding to it. So that's nice. If you have layers, you can keep on adding layers to a three-dimensional array, for instance. There are several storage drivers. Well, typically what you will use is a single file, but there are other options. So you can store it in multiple files. You can store it in multiple files on a parallel file system, although you can also use it with a single file from a parallel file system, but okay. And you can do that in memory. Again, normally single file, also single file on a parallel file system, but okay. On very large systems, parallel systems, you might perhaps use multiple files. So it can be done, but yeah, it's not relevant for us. So how do you use it? It's a library which is implemented in C under the hood. You can use it from C, from C++, from Fortran, also from Java. If you look at example code in C and C++ and Fortran, you will see that it's pages and pages of code. So it's not so trivial to use from these languages. In Python, there are two implementations, PyTables and H5Py. Both are doing HDF5 files. PyTables has a feature that H5Py doesn't have. It allows you to do Pandas data frame-like storage in an HDF5 file, which, as far as I know, H5Py doesn't let you do. But H5Py has better performance, and it's also the package which is typically used by the machine learning community. So I'm going to talk here about H5Py. If you're interested in PyTables, the slides are here. I'm just not going to discuss them. Okay, so the nice thing is I can write an HDF5 file from any application written in any programming language and read it in any other application written in an arbitrary programming language. So that's very nice. I can create an HDF5 file using MATLAB for pre-processing, then running a C++ application, and then doing an analysis of that again in MATLAB or in Python or whatever. HDF5 file can be read. So it's actually fairly trivial to use it from Python, whereas in C, C++, or Fortran, it's really pages and pages of programming. Okay, so H5Py, importing the module, import H5Py very easily, and then probably you will also need NumPy. Okay, so opening and closing an HDF5 file, very simple. You simply call the file function in the H5Py module. And that is going to give you a file handle. So H5 file is a file handle. And you specify the file name and you specify the mode. The mode can be write, W, so that's for creating a new file. It can be R for reading, and it can be A for appending. Appending means I'm going to modify an existing H5 file by, for instance, adding to an existing dataset. Okay, so this is reading. Sorry, this is appending, and this is reading. Okay, close the file is just call the close method on the file handle. Of course, in practice, you don't do that. In practice, you use a context manager. So with H5Py file as whatever, do some stuff. At the end of the context manager, also, if something goes wrong, the context manager will in fact do the close on that H5Py file. And that's for HDF5 files even more important if you're writing them, because if a write operation, if a file which is opened for write can get corrupted if you exit without closing. So basically, if you open a file for writing, always do it in a context manager so that you're that you're sure that even if something goes wrong, the file is closed. If you don't close it, you might end up with a corrupt file, and fixing a corrupt HDF5 file, good luck. That's not going to be easy. Okay, so how to create groups? Let's call it directories if you want. Very easy. You have your file handle and you use the create group function with the name of the group. Okay, that's easy. What you can also do is create a group in a group. So this gave me a group, input group. In that group, I can create a new group with the name fields. So now I have a nested group. At the top level of the file, I've got input. In input, I've got a group which is called fields. Okay. I can also do that in a different way. I can also just on the file itself, again, call the create group, but with /input/fields. So that means at the top level, I have the input group and fields is a subgroup from it. Note the correspondence to the Linux file system. The file is the root of the file system, and then consecutive directories, well, consecutive groups are consecutive directories in your directory hierarchy on your file system. So that is very similar. Adding a data set, quite convenient. I create some data set. In this case, I'm again using MeshGrid. I have a field, so I get a 2D thing, etc., etc. Okay, how do I add it to my HDF5 file? Well, in the fields group, I do create dataset. The name of the dataset is magnetic. The field values shape I must provide. So I just use the shape of my NumPy array here. And then, of course, I also need to specify the type of the dataset, and that's just by getting the D type of my NumPy array. Okay. And then I can assign the I can assign the values to the dataset just by assignment, and I can use the slicing notation here in order to copy the entire elements. And then when I'm done, I can choose to do a flush. Basically, the HDF5 library will try to optimize I/O, so it might temporarily buffer values. So decide not to write. If you want it to write, then you can do a flush. It will eventually write, but maybe you want to make sure that your data is in fact written at this point. In that case, you do a flush. Of course, that may come at a performance price. So don't just do flush each and every time. Only do flush when it makes sense. Because yeah, the fact that it buffers means it wants to optimize. If you say, okay, don't buffer right now, you take away that chance for optimization. Okay. Then adding, for instance, a two-dimensional array, yeah, that's the same because that's what we actually did. But this is a different NumPy array. So basically, this represents coordinates. And again, we have a data set, shape, etc., etc. So in fact, it's the sort of the same example. Okay, so I mentioned that we could add annotations. And for instance, to our field group magnetic, so that's our data set, we add an attribute which is called units, and which is in this case the string MT, so millitesla. So we can add annotations to any data set by using attributes as sort of a dictionary. So attributes looks very much like a dictionary. You can also add annotations to a group, same thing. So field group gets the annotation warning, don't modify for whatever reason. Okay, so attributes are mostly like Python attributes, so you can set, get, remove annotation, no problem. You can iterate over annotation names using the keys method on attributes, so that's all very convenient. Okay, suppose we have an HDF5 file, we open it for reading. How do we read a data set? Well, again, that's extremely trivial. So we have H5 file, input field magnetic, and we assign that to our variable magnetic field, and that is going to be an NumPy array. I can just compute NP average, for instance, which would give me the average value of the magnetic field, if that would make sense. Okay, I can also read a particular slice. So remember we had these coordinates positions, and so now I'm going to read all the columns, so both the X and the Y position, but only from the 4th up to the 7th element. Okay, so basically that would read the X and Y coordinates of 4 particles. I can also read non-consecutive data. For instance, in this particular case, I would read the 3rd, the 5th, and the 7th the coordinates of the 3rd, 5th, and 7th particle in my position data set. So this is using hyperslabs in Python, and I can assure you, look at the equivalent code in C, C++, or Fortran, and you will see half a page at least in order to get this done. While it's in Python, it's just a one-liner. Of course, remember that if you do non-consecutive reads, as here with these indices, you will get a performance hit. Consecutive reads are much faster, so keep that in mind. It can be useful, but it will cost you performance. Okay, so that was what I wanted to tell you about HDF5 files. There are a number of useful command line utilities that come with HDF5. One of them is h5dump, and that will give you a textual representation of your HDF5 file. Don't do this on a 20 gigabyte HDF5 file because you will be waiting for the end of the output till the end of the universe. So don't do that. This is mainly useful if you are developing applications that read and write HDF5 files. You start with small files, but this way you can see whether the data layout, your data sets, and so on are in the right places and whether everything looks fine. So it's a useful utility, but yeah, don't use it on large files. It's pretty obvious. It will create an awful amount of text. Similar libraries for R. Yes, it's called HDF5. So there must be definitely an HDF5 module for R. If you look at cron for HDF5, I'm 100% sure that you will find an R package to read and write HDF5. I'm not quite sure what you mean with a multi-language program. So if you mean that it's possible to write programs in R that would manipulate or analyze data that has been produced by a program written in Python or in C++, then the answer is yes. So if that's your question, the answer is yes. Otherwise, I'm not sure that I know what you mean by multi-language programs. Okay, so yes, it's very useful for that. By the way, if you want to visualize data sets in HDF5, you can use tools like, come on, again, my memory fails me. I'd say it's Paraview, yeah. So that's a very useful thing to visualize scientific data. So basically fields, flow fields in liquids, or temperatures in three-dimensional spaces, and so on. For such a thing, you would use ParaView, and ParaView happily munches HDF5 files. So that's also one of the major use cases. Another one is H5LS. And of course, you notice the correspondence with Linux file systems. LS will show you data sets and groups and so on. So it's nice to explore the structure of your HDF5 file. H5 copy, that just copies a data set from one HDF5 file into another HDF5 file. Can be convenient. You don't have to write your own code for it. There's a utility for it. H5 make group, just like mkdir in a file system. So you can just create a group in an existing file, again, without writing code for it. Then if you want to compile, it's not so relevant here, but if you want to compile C, C++, or Fortran code that uses the HDF5 libraries, the HDF5 distribution comes with wrappers for that. So basically, that will actually set all the flags which are required for HDF5 file for the compilers. So that's convenient. And what is very convenient is that it also, and that's where it may come in useful for you as well, if you use H5CC, for instance, show config, it is going to show you the features of the HDF5 library which are enabled and which are not enabled. And that can be very convenient to check let's say an installation of the HDF5 library, whether it contains the features you want or not. For instance, can it do parallel I/O on a particular file system? Show config will tell you, so that can be useful. Okay, so these are the equivalent slides, but on PyTables. So yeah, performance is slow compared to H5Py, but I like the implementation, and that was why many years ago I made slides for PyTable. I just recently made the slides for H5Py because it's much more performant. Okay, I'm going to skip those. Feel free to browse them at your leisure. They are still available, and I have examples for both H5Py and PyTables in the source code directory. Okay, so next topic on the list was indeed Bokeh. So Bokeh is another plotting library, and I would say it's easy to use. Nice thing is that it integrates with Pandas, which is a bit more, well, it's not tricky with Matplotlib, but a bit less natural. So that's a nice feature in a way. It's very nice to create interactive demos in Jupyter Notebooks. And also a nice feature is it will export to HTML pages with some interactivity as well. It uses JavaScript for that. So it compiles things down to JavaScript. And so I can send a Jupyter Notebook as an HTML page to someone. And the interaction with the graphics will still work. So that's kind of nice. And you've got reasonable support for LaTeX labels. It's not as good as Matplotlib though. I would say that it is more oriented towards what I would call information visualization rather than scientific visualization. It's, for me, not so much about visualizing data from physics or from chemistry, although you can, but I would position it more in information visualization, so more in data science kind of applications. So let's create a simple plot. Again, the same plot essentially as the one which we did in Matplotlib. So we import some stuff from Bokeh. We import figure, output file, and show. So we start by generating the data. No one cares. We create an output file. Okay, and that will be an HTML page in this particular case, which we give a title. Okay, Then we create a figure. We also give that figure a title. So the title is then pendulum. We define an x-axis label, a y-axis label. Notice no later here. That's a little unfortunate. And then we add a plot. So we have a line plot with x and y coordinates, which were generated here. Then we have another line plot with x and y min. And again, we set certain attributes. The line color is red, the line width is a bit less, and we want a dotted line. So that is with line dash. And then 2, 2 means my dash has a size of 2 and my gap has a size of 2. So that gives me sort of a dotted line. And I do the same for x and y min. And then I show the figure. Okay, so basically that will give me the HTML file. And this is what you should notice. This is the interaction thing. So the cross kind of thing here, it means that I can pen my data. So I can move left and right to inspect certain parts of my data. I have the possibility to zoom by selecting a rectangle. That's this thing here. I can also zoom just using the scroll wheel, well, which I can't here, of course. I can save the file to disk as a PNG, for instance, and I can reset everything. So all of these things just are present in the HTML file. So that's actually rather nice. In the browser, it will be interactive. Okay, you can also add widgets. So basically, I've got a plot here of a sigmoid function, and I can actually add here this widget by which I can control a parameter of the function. So basically, beta determines the steepness of this curve here. So it can be a bit less steep or a bit more steep depending on the value of beta. And I have a slider here in order to deal with that. And again, this is present in an HTML file. So I can, of course, do that in a notebook, in a Jupyter notebook, but also in export that to HTML and it will still work. Okay, this is a bit of programming in the sense that you have to write a callback function and that should do the right thing, and you will have to do some JavaScript tinkering as well. So basically, yeah, whether it's worth it depends on your use case. What you can also do, and that is quite powerful, you can actually, can I show it? That might be a bit more interesting. So let's see. Okay, and I should have that notebook somewhere. That's an intro, that's not interesting. This is something I should remove. Here's the notebook I'm looking for. Pendulum, yeah, that would be the one I actually want. Let's hope it works. It's always a bit tricky, but normally it ought to be okay. All right, so I'm going to, this you know, that's my set of differential equations for the pendulum. You also recognize the Jacobian. Okay, and now I write a function solve, and that is taking the Jacobian and the function of the Jacobian, maximum time, delta, so it has a lot of parameters, as you can see. And basically, what it will return is a dictionary with the variables, well, with time, the values of the function theta, the values of the function omega as lists. So these are lists. So basically that gives me the time points between 0 and t max with a certain delta, which is somewhere. Basically it solves my set of differential equations. Okay, so now I have the function that creates the plot. So basically that's going to create 3 figures which are interlinked, and which have this update function. This update function is a callback, and that is going to be used interactively with this slider here, which basically allows me to set the length, the damping factor, the magnitude of the driving force, the frequency of the driving force, and so on. And the integrate, that will give me a list of sliders, well, a sequence of sliders. And if one of these values is changed, the update function will be called. And that update function will then recompute all the data, and the plot will be changed accordingly. Okay, so let's call that function. Okay, so as I said, I get three plots. One shows theta as a function of time, the other shows omega as a function of time, and the last plot shows omega versus theta. So that's your phase space essentially. Okay, now I lack screen real estate, but let's increase the damping. Okay, and normally things should change, but they don't seem to. Why not? Okay, it ought to get recomputed. I don't know why it's not doing it right now. Yeah, normally my solution should get recomputed, and this should be the plot should adapt interactively, but it's refusing to do that. It is possible that I'm missing a software component here. I'm not sure whether I have IPyWidget installed, which I would need under the hood in order to do that. So that's possible. And that's a little bit the problem with this package. Now it works and now it doesn't. That's a little annoying. But you see where this is going. So normally this should work. It's likely something with the installation, which is not quite okay. Anyway, so you can do different things as well. This is, if the previous one is not going to work, this one is also not going to work, but at least I can show you the plots. So basically, here again, we have three connected plots. And what I should be able to do is select data points here and get the corresponding data points in the other plots. But again, that does not seem to work. I'm going to select this and see. Ah, this works. Okay. So I can select data points here, and the corresponding data points in the other plots are going to be shown as well. So why does this work and the other does not? That is bizarre. Okay, I have no idea. Okay, I don't get it. Don't know why it doesn't work. Should work, but apparently it doesn't. Okay, anyway, so that's another thing. You can easily explore data with that. Of course, it requires some programming in the sense that I have to link my plots. So basically, I have to make sure that this is all set up correctly. I'm not going into the details. I would say look at the code at your leisure, and you will see how it works. This is the last example. So basically, again, this is a scatter plot, but now if I hover over a point, I get annotation. Because in this plot, omega versus theta, the time information actually is not visible. But I can show that by showing a pop-up each time I hover over a point. So I can actually see the time value and also, of course, the precise theta and omega values at this particular point. So basically here we are at 13 seconds into the movement of the pendulum. Okay, so that works. as well. So why on earth does this not work? That is very bizarre. No, it doesn't work, and I really, really don't know why. That's strange. Okay, anyway. Probably it's also not going to work. I have another example, but it would be weird if that were working. If the other isn't, but who knows? Okay. So that is just an ordinary plot. And then we have a theoretical model. Okay, all right. So here's my plot. And now I can, where are my sliders? Here is the interactive thing. Okay, so let's see. If I play with these, does something happen? No. Apparently I'm missing a package in my installation here. It also doesn't work. Yeah, I would have been surprised if it worked, but okay, one can hope. Okay, should work. Have to figure out what's going wrong, but you get the idea. So these are things which you can do with Bokeh for interactive plots, and if everything is installed well, then it actually works. So these slides do the same thing as I show the same thing as I already told you about. Okay, so that would bring us to image and video processing. Any questions about Bokeh? Let's start with that. Okay, will you update? Well, I don't think it's a matter of updating the notebook. It's a matter of checking what I'm missing from my Python installation. So I think I'm missing a component in Jupyter Lab, which allows for this interactive stuff. That is probably not installed or not installed properly or something with versions. So the notebook itself ought to be fine. It's just something in the Jupyter Lab installation, I think, which is missing. It's always tricky, and the problem is that the Jupyter Lab people are also not always helping, in the sense that they sometimes change stuff which ships with Jupyter Lab, and then you have to install it, and you don't notice that it isn't there because you didn't use it for a while, etc., etc. So that's what I think is going on here. So the notebook should be fine. It's just the Jupyter Lab installation, which is likely missing a plugin. That's my guess. But yeah, I'll try to get it working at some point. And if something needs to be updated, then of course I'll do that. So can we, instead of sliders, select between three values? Yeah, so basically the whole slider thing is part of IPy widgets, and you have many widgets. So indeed you can have, for instance, radio buttons, which allows you to switch between values. That's entirely possible. You can also add a text field where you can just enter a string, which then, for instance, gets converted into a number, or which gets translated into a category or something like that. You can have elements that let you select things from a list, so a drop-down menu, either with single selection or with multiple selection. So IPy widget is really, really powerful. It allows you quite a lot of interaction in notebooks. And by the way, that is also independent of Bokeh. You can use this with Bokeh. You can also use IPy widgets just with Matplotlib. It's also possible. And it's actually very easy to do. So you don't even need Bokeh for that. Okay. So, image and video processing, not that much. Again, the message here I'll give up front. Basically, these libraries which I'm going to talk about are quite good. In the documentation, you always find references to the algorithms. So if you are not that familiar with image processing or video processing, then it's a good idea to read up on the algorithm to see what it's actually doing. And again, you can do rather complicated things in a very short period. Okay, so there are many ways to well, there are many relations between image processing, video processing, and Python. For instance, it's possible to use dedicated software, GIMP, OpenShot, and so on, and use Python for plugins. So you can write your own plugins for these programs using Python, which allows you to do specific processing if you are into that. Alternatively, you can also use Python to do scripting. So, for instance, to do certain image transformations based on certain properties of that image. So that's quite possible, and it's not what I'm going to talk about because that's very application specific. So if you want to do that, check the documentation of GIMP or OpenShot on how to write plugins. Also, for the life of me, I wouldn't know what type of plugin to add because typically these things come with much more than I even know about. So to roll my own, it's not for me. Okay. On the other hand, you can also do image processing in Python itself. Then you have a number of libraries. One of them is Pillow, and that's basically a very basic image processing library. And yeah, it's used under the hood by quite a number of other libraries. There is scikit-image. That's much more sophisticated, so it has quite some sophisticated algorithms, and this is what we will talk about. And then there's also OpenCV, and you can use OpenCV on the one hand for image processing, but also for video processing. So it's quite comparable for image processing with scikit-image. But I'm not going to talk about image processing with OpenCV. And then for video processing, there's mainly OpenCV, and that has quite a lot of very nice algorithms. So I'm going to talk about scikit-image, and I'm going to talk about OpenCV. Okay, so one of the things which you might want to do is image restoration, in the sense you have an image and the resolution is not particularly good, or it's a bit blurry or something like that. So this is our original image. By the way, that comes with scikit-image. It's one of the sample images they ship it with. And I want to make this image a bit crisper. Okay, so I can do that using a convolution. And this is basically going to be the convolution, the kernel of my convolution. So I'm starting with a very stupid kernel. It's basically a uniform kernel 5 by 5, and it's normalized to 1. So this will definitely not sharpen my image, that's for sure. It will not do anything interesting except blurring things. So that's definitely not what we want to use, but it's a starting point. Because what we're going to do is to use an unsupervised Wiener algorithm, and that starts with our point spread kernel, but it is going to learn a better kernel. And the kernel it learns, and unsupervised means it's going to actually determine the optimal kernel itself. It's going to apply that to the image, and that will give us a denoised image, a somewhat sharper image. So basically our image is going to be either, in this case, a two-dimensional image because it's grayscale, or a three-dimensional image where we have RGB values for each pixel. Okay, so this can be, in this case, it can be a 3D numerical array, or in this case, I think it was just a two-dimensional one. All right, and this is the result. So I'm not sure whether you can see it, but at least on my screen, it's clear that the nose is a lot sharper. The eyes are sharper. There's more detail in the hair and so on. So yeah, with basically 2 lines of code. And this is quite impressive. Okay, and for image I/O, it also has quite a library. So there is an I/O module. You could use SciPy I/O for that, but basically, if you're doing images, then maybe SK Image I/O is the better choice. Okay, so that was very easy. A bit more difficult is image segmentation. So what we're interested in is the face of the astronaut. We're going to use the same image again, but now we want to have the face of the astronaut. What we're going to do is again define a rough initial contour, and that's basically just a circle around the head of the astronaut. So that's what I'm doing here. Basically, you recognize the x and y coordinate of a circle with center x0, y0. Okay, and that initial contour, well, the contour is going to be called a snake. So this is the initial snake. And as you can see, it's the blue dashed circle here. All right. And then I'm going to use an active contour method. And I give it the image, the initial snake, and some values alpha, beta, and gamma. And those will determine how much the snake basically how closely this snake follows the face of the astronaut and so on. So basically, these are parameters which you need to tune a little bit. That is why actually in the documentation of Active Contour, there is a reference to the original research article that introduced this particular method. And you can read up there what the semantics is of alpha, beta, and gamma. I did. I don't remember, so don't ask. I forgot. But basically, it's there. And when you tune a little bit these values, you see that the results improve depending on your choices. So again, this is quite simple. How well does it work? Well, basically, don't know whether you can see it, but there is a red line here around the head of the astronaut. And it's doing quite well, except at the ears. There's a little bit of background at the ears here. But that's the only, I would say, minor point where it doesn't really follow the face correctly. Probably fiddling a bit more with alpha, beta, and gamma could potentially improve this. So yeah, again, a few lines of code in order to determine our initial snake, and then one line of code to get the result. Except for one thing, if you look, and again, that's why you need to look at the documentation. If you look at the documentation of Active Contour, it's going to tell you, well, okay, don't do this on the original image that you actually want to segment, but first smooth it a little bit. Okay, smoothing is very easy. You can use a Gaussian kernel for that, which is predefined. And basically, I can smooth the image by using Gaussian image, and I use a 3x3 kernel here for my convolution. Could do that by hand, but yeah, okay, why bother if there is the Gaussian function that does it for me. And that's going to smooth my image a bit. Okay, so that's why you need to read the documentation, because otherwise you may get suboptimal results. Of course, there are many more tasks in image processing, and again, you can talk a whole semester about image processing alone. So this is just to give you a flavor, and again, to show you that with few lines of code, and of course, knowing what you do, so read up on the algorithms, that you can actually do things very, very fast. Okay, let's talk about video processing. So the first thing is you can capture video from a USB camera, for instance, and it's very easy. You import CV2, so that's OpenCV, and then you use device 0 for video capturing. So if you have only one USB camera, that is going to be device 0. If you have two, there will also be a device 1. So you can choose from which device to capture. Okay. And then we have an infinite loop, and we're going to read a frame. So on the capturing device, we're going to call the read method, and that is going to give me two things, the status and the frame. So if the status is non-zero, then we have a problem. Some error handling needs to be added here. So I could do many things. In this case, I'm doing something very stupid. I'm just going to show each image on the screen. That is this I'm doing with CV IAMShow, so image show. The name of that is frame, and I'm going to display the frame. And then there is also functionality to wait for a key press. So if a key was pressed and that key happens to be a Q, then I stop this loop. So I'm going to record as long as I don't press the key. Well, I'm not going to record. I'm going to capture a video image of my USB camera up to the point where I press Q, and it's going to be displayed in a window shown on my screen. So that happens. When I'm done, of course, I should destroy all windows. That takes care that the IAMShow thing, which creates the window on screen, is actually properly destroyed. And of course, I should also release the capture. So basically, I should release my device so that, for instance, Teams can use it for my next conf call. That's kind of important. Okay. Now, one thing which you should note is that for whatever reason, a frame in OpenCV is not RGB, but BGR. Okay, so your red and blue are in fact swapped. Why? No idea, but you need to be aware, because otherwise you mix up your colors, and that's probably not what you want. Okay, so I can also write a video file just by CV2 video capture. I put it to a file, it's very easy, and then I can write frame by frame to the video. So that's very easy. I have to specify the frame rate, obviously, because that's part of the file, and I have to also specify an encoding, which is here. Again, something you need to look up in the documentation. This is Xvideo. You might need another codecs, but that's something that you need to look up in the documentation. Okay. Apart from that, there is not so much interesting here. Let's move on to an example. So this is code which will actually follow a ball that bounces around in a video. So I create an original frame, which is the track window. And this I just, I initially put it around the ball. And then I'm going to use an algorithm that actually follows that ball. It will keep the frame around the ball as it moves through the video. We'll see that later. So basically what I need to do is to create an HSV frame. So basically I got my BGR. I want to go to HSV. So this is a conversion from HSB to from BGR to HSV. HSV is another way to describe colors. So that's hue, saturation, and value. So the hue is essentially the color. The saturation is how intense it is, and the value is how bright it is in a way. And this is a much easier color space to do color manipulations in rather than RGB. So basically I create a mask, and that mask is set on the hue. So I want the hue between the minimum value and the maximum value. And I don't particularly care about the saturation and the what is it, the value. So this is just between 50 and 255, while the hue is restrained in these values here. Okay, then I'm going to calculate a histogram on my frame, and this is the first frame of my video, and I'm using a mask again based on the minimum and the maximum hue. Okay, that will give me a histogram in terms of my color space. And then I have to normalize that quite easily. That histogram gets normalized between 0 and 255, and I want the min-max normalization. Okay, so the hue determines the color, that's the important thing. And we want only a histogram for the color. Then I read the frames one by one. I have a termination condition here, which doesn't matter that much, but I'm reading my frame and I'm using the mean shift algorithm. So basically here I'm doing a back projection. So essentially I'm going using my histogram. I'm actually going to select pixels in my frame, which correspond to the colors I'm actually interested in. And again, I'm doing the conversion from BGR to HSV. Okay, and then I'm just going to have my tracking window iteration by iteration. Okay, let me show you. So basically, this is my initial frame, the blue thing, and the yellow ball is what I want to follow. And as you see, it does that pretty well. Now it's going to jump, and it's again going to jump. It loses it for a few frames, but then it gets it back. Okay, so you've seen the entire code to do this. So again, this is something that is really trivial if you know which algorithm to use, if you understand how the algorithm works. So basically, this is just a small illustration that you can do sophisticated things here. Okay, so the documentation is really, really good, and I would encourage you to check it. Okay, this is the end of this particular training. Are there any questions left? If not, we will conclude here because I need to teach in half an hour and I need to move to another building. You cannot download the recording, but you can send me an email and then I'll give you a link to the recording. So feel free to mail me if you want a recording, no problem. It will be available only by somewhere tomorrow because some processing is needed and it takes a while. Okay. The program for next week. Just look at the website, please. I really have little time now, so I would prefer to actually leave because I need 20 minutes transit time. Okay, maybe see you next week, and I hope you enjoyed the training. See you later.